Let us now start the chapter of fluid kinematics. Now the word kinematics basically deals with motion without any reference to forces. So you can say that in fluid kinematics, we are going to study the fluid flow without considering the forces influencing the flow. You see, the previous chapter was dealing with fluid statics, that is when the fluid is at rest. But from here onwards, we are going to expect flow taking place. But while the flow is taking place, you are not creating any reference whatsoever to the forces causing the flow. That is fluid kinematics for you. So you can say the definition of fluid kinematics as study of fluid flow, without considering the forces causing the flow. Without considering the forces causing the flow. So this is a brief idea of the subject we are having. Now let us look at the overview of this subject. What do we study in this subject? The first thing we are going to study under fluid kinematics is approaches. What do I mean by approach? The study of fluid kinematics is going to have two approaches, two ways of approaching the subject or methodology of approaching the subject. These two approaches are known as Lagrangian approach and Eulerian approach. Over here we'll be seeing the differences between these two approaches. After having studied approaches, the second thing we are going to study over here is the concept of velocity. Please remember, in the entire subject of fluid kinematics, velocity happens to be the most important parameter. If you want to study classification of flow, it depends on velocity. If you want to study continuity equation, depends on velocity. Acceleration concepts depend on velocity. Any way of visualizing the flow like streamlines, path lines and all depend on velocity. Any concept of rotation or deformation of a fluid element again depends on velocity. So you can say that everything over here is somehow surrounding velocity. After studying velocity, we will study something known as classification of flow. Classification of flow. Classification of flow. Over here we will be classifying the flow based on how it is varying with respect to space, time, etc. After studying classification of flow comes the most important topic. There is no topic in this chapter which is as important, even though I say velocity happens to be the center of this subject. But importance wise, this topic is very important, and that is known as continuity equation. Continuity equation. Over here we'll be talking about law of conservation of mass applied in a particular flow. After studying continuity equation comes the next topic, which is known as acceleration. Now you can say that whatever I have mentioned till here represents one part of the subject. After completing this part of the subject, you'll be starting the second part, which deals with how to visualize the flow. To visualize the flow, we are creating certain patterns. We will see what these patterns are. The first pattern we are mentioning over here is known as streamline. The second pattern is known as path lines. The third pattern is known as streak lines. And the final pattern is known as timelines. These are certain patterns required for studying or visualizing how the flow is taking place in a flow field. Amongst all these patterns, the most important pattern happens to be streamline. And based on streamline, you'll be studying one more topic, very important topic, known as stream function. Stream function. Stream function. Now this completes the second part of your chapter. Second part is completed till here. What do we study after this thing? After this thing, you are now going to talk about how the deformation in a fluid element takes place. Please understand that a fluid element is going to continuously deform in a flow. That is a primary difference between a solid body and a fluid body. A solid body experiences only static deformation. That means under a particular amount of shear stress, it experiences some shear strain and then keeps quiet. Where in the case of fluids, under a particular amount of shear stress, the fluid will keep on undergoing shear strain. That is why rate of strain becomes important. Over here, we are going to study two types of rate of strain. The first rate of strain we are going to talk about is known as rate of linear strain. Rate of linear strain. The second thing we are going to discuss about is known as rate of shear strain. Shear strain. These two strains we are going to discuss. After studying these two strains, we will be studying one more topic that is called as rotation. A fluid element can as well rotate in a flow field. While it is moving in a flow field, it can also rotate. That we are studying in rotation. And under the concept of rotation, again you'll be classifying the flow. And when you classify the flow, you'll be having a flow called as irrotational flow. For irrotational flow, we define one more function with which we'll be closing this chapter, and that function is known as potential function. Potential function. Now, this chapter is a highly mathematical chapter. So, I would recommend you, before you start studying this chapter, please go through some basic mathematics. What part of mathematics is important? I'll mention over here, so that you can refer to from your mathematics classes. I would recommend you to go through basics of calculus, and under calculus especially, you should go through partial derivatives. Partial derivatives. Basic idea of derivatives is sufficient. Apart from this, I would also recommend you to go through kinematics kinematics from your engineering mechanics syllabus. Engineering mechanics syllabus. This will be helpful for you to understand our subject. Now let us come towards the important factor. You see, any examination you write, you will be having mostly one question at least coming from fluid kinematics. No matter you belong to a mechanical background or a civil background, you will be having questions coming very frequently from fluid kinematics. You can say, if you look individual chapter wise, you can say that this chapter happens to be the most important chapter from examination point of view in entire fluid mechanics syllabus. And one more thing is, if you understand this chapter, it will be easier for you to go through advanced courses in fluid mechanics syllabus, which will be important if you are taking up these courses in your MTech level. Now let us discuss the approaches in the case of fluid kinematics. So let me mention over here approaches. I have already mentioned that there are two approaches to the study of fluid kinematics. The first approach is known as Lagrangian approach. The second approach is known as Eulerian approach. Some people pronounce it as Eulerian, but Eulerian is the exact pronunciation. Let us see the differences between these two approaches. Now, what do we mean by Lagrangian approach? What do we study in Lagrangian approach? Please understand, the problem with fluid kinematics is you are not having a single particle flowing, but you are having a system of particles. All of them are flowing. Probably they are dependent on each other's flow or they are independent on each other's flow. So these particles, please imagine them, they are randomly moving. To visualize such a flow becomes very difficult. That is why we are demonstrating two approaches over here. First approach, Lagrangian approach, over here is a particle-oriented approach. It is a particle-oriented approach. Particle-oriented approach. Now, what do I mean by this particle-oriented approach? By particle-oriented approach, we mean that in a flow field, we are choosing a particular particle and we are studying how the motion of this particle is taking place over a period of time. So let us say I have over here a flow field. This is a flow field, let us say. In this flow field, I am having many fluid particles randomly moving. But I want to study only Lagrangian approach over here. So what I do is, I choose a particular particle in a flow field. Let us say this particle over here is my subject particle. I am concentrating only on this particle. Let us say the particle is present over here at some time t equal to 0 seconds. Now I observe that this particle is moving in a flow field some way like this. Let us say the particle has reached over here at some tth second. I am only observing how this particle is moving. This kind of approach where you are not concentrating on all the particles, but you are concentrating only on a particular particle or a set of particles, that is known as Lagrangian approach. That is why I also call it as particle-oriented approach. Now come to Eulerian approach. How do we study over here? Under Eulerian approach, you are going to have position orientation. It is a position oriented approach. Position oriented approach. Now what do I mean by position oriented approach? Imagine you are having a flow field. You are having a flow field. In this flow field, you have a set of fluid particles, or let us say a numerous amount of fluid particles which are randomly moving. Now you think practically that at any position there should be some fluid particle present. For example, if I choose a particular position over here, let us say if I choose a particular position somewhere over here, there should be some fluid particle present now, next second, next second. Likewise, every instant there will be some fluid particle present. Of course, different fluid particles, but they are always going to be occupied. These positions, every position is going to be occupied by some fluid particle. So the logic in this Eulerian approach is, instead of defining the parameters for the particle, let us define the parameters for the positions. So for example, I will say the velocity at this position is so and so. When I say velocity at a position is so and so, it does not mean that the position is moving with a particular velocity. It actually means that the position right now is giving this velocity to the particle present. Let us say this hand over here represents a position, and let us say this fist over here represents a particle. Now this particle has come into this position. If the particle comes to this position, this position is allowing some velocity. So the particle will take that velocity and move forward. Once this particle has gone, another particle will come over here. Likewise, every position is going to have some particle occupying it. So instead of defining parameters for particles, we are defining parameters for position. I hope this is clear to you. That is why I call this as position oriented approach. Over here, every parameter is defined for position instead of being defined for particle. This is a primary difference between Lagrangian approach and Eulerian approach. Now come to mathematical difference. Coming to mathematical difference, a Lagrangian approach equation, standard equation, is represented something like this. It is represented as this equation. What does this equation say? It says that identity of a particle, this S over here, represents identity. Whose identity? Since it is particle oriented approach, identity of a particle. Identity of a particle has to be dependent on initial identity. Initial identity and time. Identity of a particle is dependent on initial identity and time. What is the meaning of this thing? You can say that at any particular point over here, let us say this particle is moving like this, at any point over here, there is some velocity. There is some velocity. The particle is having some velocity. Now my question to you is, how do I write the equation of this velocity? To write the equation of anything, you should know what is this depending on. So this equation over here says that the velocity should depend on initial velocity. Let's say V0 is the initial velocity. And how much time has taken place from here to here. So I can say that velocity is a function of initial velocity and time. As a matter of fact, you have seen these kind of equations. You have seen these kind of equations. For example, when you study mechanics, engineering mechanics, and you are having a uniform acceleration motion. In uniform acceleration motion, you might have come across equations like V is equal to U plus AT. Now if you observe over here, what is this V representing? V is representing velocity, and this velocity is a function of what right now over here? It is a function of u, and u stands for initial velocity. Initial velocity. Apart from initial velocity, it is depending on what? It is also depending on time. It is also depending on time. Now, if you look over here, this equation I have written, which is a very, very primary equation, very basic equation in your mechanics, is very similar to the equation, standard equation of Lagrangian approach. So this is regarding the concept of Lagrangian approach. Now come to Eulerian approach. How is the equation written over here? Very simple equation. It says that identity is a function of space and time. Now the question is, whose identity is this? Whose identity is this? To understand that, if you see, Eulerian approach is a position-oriented approach. If it is position-oriented approach, then I should say that this is the identity of position. The identity of position happens to be a function of space and time. That means velocity, acceleration, all these identities, they are going to depend on space coordinates and time coordinates. So this is the concept of approaches in the study of fluid kinematics. Now next thing, from your examination point of view, you should know that which approach is more commonly used. Please remember, it is Eulerian approach which is commonly used. Lagrangian approach, even though it is going to have its own benefit, everything has its own pros and cons. But from our examination point of view, from our subject point of view, we prefer going for Eulerian approach more commonly. Of course, you can have questions coming from both these things. After studying the approaches, now let us talk about velocity. I believe everyone knows the definition of velocity, but let me still define it. Definition of velocity. You can define velocity as time rate of change in displacement. Time rate of change in displacement is known as velocity. Further, remember one more thing, that velocity happens to be a vector quantity. It is a vector quantity. So I can say velocity vector is equal to ds upon dt. Now these are very fundamental things which you have studied probably from your schooling level itself. So till here, nothing to do with fluid kinematics. This is basic physics which defines velocity. Now let us move further to our subject point of view. If I want to define this velocity, I can define this velocity in Eulerian approach based on two coordinate systems. One coordinate system is known as your Cartesian coordinate system. The other coordinate system, which again is a part of your syllabus, is known as cylindrical polar coordinate system. So let me start with Cartesian coordinate system. Now this we are studying is for fluid kinematics. So let us see A bit. A bit. Velocity in Cartesian coordinate system. Velocity in Cartesian coordinate system. Now, what is the equation of velocity in Cartesian coordinate system? The equation of velocity is something like this. Velocity vector is equal to ui cap plus vj cap plus wk cap. This is the equation of velocity in Cartesian coordinate system. Equation of velocity in Cartesian coordinate system. Now let us discuss this in detail. This is the entire velocity vector, and u, v and w are the components of velocity vector. The component u is in x-axis, component small v is in y-axis, and component w is in z-axis. So this velocity vector v is a combination of three parameters, that is component in x, y and in z. This component or this vector v, velocity vector v itself is a function of space, that means x, y, z. Apart from space, it has to be a function of time. Where am I writing this from? Please recall, when you have studied approaches, in Eulian approach, we have already mentioned that any parameter is supposed to be a function of space and time. From there, I am saying that velocity vector is a function of space and time. Why did I mention x, y, z? The reason is, when you talk about Cartesian coordinate system, over here the space coordinates happen to be x, y and z. These are the space coordinates in the case of Cartesian system. Now, once I mention this thing, I can now say that if the parent vector is a function of these things, even the components of the parent vector should also be the function of same things, which means u, which strictly is equal to dx by dt, should also be a function of these things. So let us say f1 of x, y, z and time. Likewise, small v, which is equal to dy by dt, is equal to, let us say, some function f2 of x, y, z and time. Finally, I can say w, which is dz by dt, is equal to f3 of x, y, z and time. Now, it is not compulsory that u, v and w should be functions of all these things. They might be functions, they might not be functions. We are writing a general equation over here. So this is your parent vector and these are the components of your parent vector in the case of Cartesian coordinate system. Moving further, we now have velocity in cylindrical polar coordinate system. Cylindrical polar coordinate system. Cylindrical polar coordinate system. Now, before we go any further, let us first of all define what are the space coordinates in the case of cylindrical polar coordinate system. Please remember, In cylindrical polar coordinate system, the space coordinates are r, theta and z. R stands for radial direction, theta stands for tangential direction, z of course is z-axis. Now what is the equation of velocity? Let me mention the equation of velocity. Equation of velocity. The velocity vector over here is equal to Vr, that is radial velocity in r cap, plus V theta, that is tangential velocity in theta cap, plus Vz in k cap. This is the equation of velocity in the case of cylindrical polar coordinate system. Again, let us mention how they are dependent on space and time individually. Let us start with this V over here. V vector itself should be a function of r, theta, z and time. Vr, which is radial velocity, it is equal to dr by dt. It is going to be a function f1 of r, theta, z and time. V theta, over here many people do mistakes. V theta, generally people might be thinking that V theta is equal to d theta by dt. D theta by dt. Let me tell you that this is wrong. This is wrong. Why is it wrong? Let us discuss now. You see, d theta by dt is actually equal to omega. Theta is an angle. The rate of change of angle with respect to time is going to give you angular velocity. So this omega over here is angular velocity. Angular velocity. Whereas we do not want angular velocity. What we want is known as tangential velocity. If you recall tangential velocity, it is supposed to be equal to r times angular velocity. Therefore, V theta is supposed to be equal to r into d theta by dt. So now what we are going to do is, we are now going to write this as, r into d theta by dt. Please remember this thing, very important. Now r d theta by dt, this also is a function of r, theta, z time. Finally, you are having Vz. Vz is equal to dz by dt. You have seen this previously also. This again is function f3 of r, theta, z in time. As I have mentioned previously, that it is not necessary that all of them should be functions of r, theta, z in time. They might be, they might not be. You don't have to worry about that. You just need to know the general equation. So this is the equation. This is representing the equation of velocity in the case of cylindrical polar coordinate system. Now, after having seen the concept of velocity, let us look at the concept of classification of flow. So let me write down over here. Classification of flow. Classification of flow is a very important concept. Questions sometimes can be tricky from here. Now we are going to classify flow based on time variation and space variation. So based on these variations, we are having two types of classification. The first category of classification is known as steady and unsteady flow. Steady and unsteady flow. Steady and unsteady flow. Now, what do we mean by this steady and unsteady flow? Now, let us say in the case of steady flow, if we define steady flow, it is understood what is unsteady flow also. So, let us define steady flow first of all. Steady flow is defined as a flow in which a flow in which velocity and other hydrodynamic hydrodynamic parameters do not fluctuate with respect to time. Do not fluctuate with respect to time. So such a flow is called as steady flow. So in the case of steady flow, velocity vector is not going to be a function of time. If it is not a function of time, we call that flow as steady flow. Similarly, if velocity vector happens to be a function of time, we call that flow as unsteady flow. So I can write over here, this flow over here is steady flow, and this flow over here is unsteady flow. Apart from this classification, the next classification we have is known as uniform flow and non-uniform flow. It is known as uniform or non-uniform. Uniform flow and non-uniform flow. Non-uniform flow. How do we define this thing? How do we define? Again, if I define only what uniform flow is, non-uniform flow is understood for us. Let us see what uniform flow is. Uniform flow is defined as a flow in which velocity does not fluctuate. Velocity doesn't fluctuate or change with respect to space. With respect to space. Now this implies, if I mention that I'm having a flow where velocity is not a function of space coordinates like x, y, z or r, theta, z and so on, then I would call such a flow as uniform flow. This flow would be called as uniform flow. I would call this flow as uniform flow. What if I'm having velocity varying with respect to space coordinates? Imagine a flow in which velocity varies with respect to space coordinates. I would call such a flow as non-uniform flow. It would be called as non-uniform flow. It is called as non-uniform flow. Now, one interesting thing regarding uniformity and non-uniformity is, imagine you are having a flow which is viscous, in which Newton's law of viscosity is valid. So let us say a viscous flow. I'm taking an example over here. Example of a viscous flow. Viscous flow in which Newton's law of viscosity is valid. Now you have to think and tell me whether this flow is going to be uniform or non-uniform. Now you see, viscous flow I have mentioned. That means straight away you can say, if Newton's law of viscosity is valid, tau is not equal to 0, and this value of tau is equal to mu times du upon dy, which further implies that this du by dy cannot be equal to 0. This du by dy is not equal to 0. What does this imply? It implies that this implies further that u over here is a function of y-axis. If u is a function of y-axis, tell me which category is it belonging to? Is it belonging to not a function of space or a function of space? This you see, it is belonging to velocity being a function of space. If velocity happens to be a function of space coordinate, for sure the flow has to be a non-uniform flow. Therefore, whenever you see a viscous flow taking place, assume straight away that the flow, not assume, rather be sure that the flow is going to be a non-uniform flow only. Apart from this classification, we have one more classification, and that classification is 1D, 2D or 3D flow. This classification is 1D, 2D or 3D flow. Now there is nothing much to say regarding this. This is a very simple classification. 1D, 2D or 3D flow depends on how many dimensions, space dimensions, flow parameters are going to be a function of. For example, if let us say your velocity vector is a function only of one axis. Okay, only of one axis. If it is basically experiencing a flow only in I-axis or something like that, then you can say it is a 1D flow. The next thing we are discussing is continuity equation. Now, what is continuity equation saying? Please understand that the most basic law in physics is law of conservation of mass. Law of conservation of mass is having a result in our subject, which is continuity equation. So now you can say the result of law of conservation of mass, law of conservation mass in a fluid flow. In a fluid flow is continuity equation. Continuity equation. Now, before we start discussing about continuity equation, let us define some parameters. The first parameter I'm going to define is known as mass flow rate. So let me define a parameter over here, which is mass flow rate. This mass flow rate is represented m dot. It is represented by m with a dot. Now, what is the meaning of this mass flow rate? Mass flow rate basically means amount of mass crossing a section per unit time. Amount of mass crossing a section per unit time is known as mass flow rate. Now, let us imagine that you are having some passage like this. Let us say the flow is taking place in this direction. Now, since the flow over here is taking place in x direction, let us say the velocity over here is equal to u. Let us say this over here is a height capital H and this is some length L. If I want to calculate how much is the mass flowing per unit time, then I can say m dot over here has to be equal to. Now, what should the formula over here be? It should be equal to density times area times velocity. V over here represents the average velocity of flow for that particular area. So in this case, the value of m dot would be equal to density times. Over here, the cross-section area in which the flow is taking place. That cross-section area is equal to H times L. So H times L, and the velocity over here is equal to u. So this would be the mass flow rate. So please remember, the formula for mass flow rate m dot is rho AV. In this formula, one more thing which is very important to remember is V over here stands for average velocity of flow. Average velocity of flow through the cross section. Through the cross section. Average velocity of flow through the cross section. Now, apart from this mass flow rate, there is one more thing that is important for us to remember. Achha, before going any further, please tell me what should be the SI units of mass flow rate? The SI units of mass flow rate. SI unit. Now you see, mass flow rate is mass per unit time. Therefore, SI unit is supposed to be kg per second. Now, after having discussed this mass flow rate, let us move further. The second thing we have to discuss over here is known as volume flow rate. Or it is also called as discharge. Volume flow rate or discharge. This volume flow rate or discharge is given by capital Q. Very, very famous topic, discharge. How do we define this discharge or volume flow rate? It is defined as amount of volume crossing a section per unit time. Amount of volume crossing a section per unit time. This is known as volume flow rate or discharge. What is the formula for discharge? The formula for discharge Q is given by area times velocity. A into V gives you discharge. A over here stands for cross-section area and V again is the average velocity of flow. It is the average velocity of flow through the cross-section. You can see that if you compare this Q formula, that is AV, with mass flow rate formula, you can also say that Q has to be equal to m dot divided by density. And what are the SI units of Q? What are the SI units of Q? SI unit is going to be meter cube per second. For volume, it is meter cube. Flow rate means per unit time, therefore per second. Now, in the same case, if you look for how much is the value of discharge, it would now be equal to area, that is L times H multiplied to velocity over here. Let us say is U. Now, these two parameters are important to understand continuity. Now, let us continue with continuity equation. In continuity equation, we are going to talk about the derivation of continuity equation for Cartesian coordinate system. So, let me write over here continuity equation in Cartesian coordinate system. Continuity equation, Cartesian coordinate system. Now, for deriving this continuity equation in Cartesian coordinate system, we have to first take a diagram to understand this thing. Let us say this is a 3D space I am taking in a flow field. Let us say this is x-axis, this over here is y-axis, this over here is z-axis. In this 3D space, I am choosing a control volume, a small amount of volume of space in which I am observing the flow taking place. Let us see. That small volume is something like this. This is a control volume. It's a parallelepiped cuboid, let us say. The length over here is equal to dx. The length over here is equal to dz. This is equal to dy, let's say. This is a cuboid I'm having. Now, please imagine that this cuboid over here is an imaginary volume I have chosen. The value of this imaginary volume is equal to dx times dy times dz. This imaginary volume I have chosen. Now, this imaginary volume is having 6 faces. Of these 6 faces, there are 3 faces of entry and 3 faces of exit. So you can imagine that this is a face of entry through which there is some mass entering. Let us say the mass entering over here is m dot in x-axis. Velocity, let us say, is u. Now in x-axis, mass is exiting from here. So this is a face of exit. Now the mass flux over here is m dot in x plus dx. M dot in x plus dx. Likewise, I am having some entry over here. Let us say this is entry in y-axis, m dot in y-axis, and this over here represents exit in y-axis, so m dot in y plus dy. Similarly, you are having m dot in z entry, m dot in z plus dz exit. Please understand that it is not important, it is not necessary that whatever is the entry, same should be the exit. Imagine something like this. You are having a room. In a room, let us say you are having, or to a room you are having 2 doors. From one door, there are some 10 people entering, and from the other door, there are some 8 people exiting. So let us say entry is 10, exit is 8. Then what will happen? What will happen is, inside the room, the number of people will increase by 2 people. Is that not? Something is happening over here. The moment mass flux entry and mass flux exit are going to be different, inside there is going to be change in the amount of fluid. Therefore, density differences will be developed. That is what we are doing in this equation over here. Now, to understand this, let us write down the equation of mass flux in x-axis. So mass flux in x-axis, m dot x has to be equal to how much? Very simple. M dot x has to be equal to density multiplied to area. Area, if you remember over there, it was equal to area, if you see, it is equal to dy times dz. So I can write over here dy times dz multiplied to the velocity of entry over here is u. So this is the amount of mass flux. So let me save this as influx. Influx. Now what about influx? Basically means entry. Let me otherwise say influx in x-axis. Influx in x-axis. Now, if you see in x-axis, you are having m dot in x plus dx, that is exit. This value has to be equal to m dot in x plus rate of change of m dot in x with respect to x-axis multiplied to dx. Now this is going to be equal to, density into dy times dz multiplied to u plus rate of, that is dou by dou x of density times dy times dx, sorry, dz, I'm sorry, dz times u multiplied to dx, multiplied to dx. Now if I calculate this thing, it comes out to be equal to density dy dz times u plus dou by dou x times density into dx dy dz whole times u. This is a value. Now please observe over here that dx dy dz is equal to the volume, and this volume over here is a constant. So what I can do is, I can now say I can now say that the value of m dot at x plus dx has to be equal to density into dy times dz multiplied to u plus. Since it is a constant, I'm bringing it outside. So differential volume in dou by dou x of rho into u. This is a value. Let me call this as efflux in x-axis. Efflux in x-axis. So basically the entry was equal to rho dy dz into u. Exit is equal to rho dy dz into u plus an extra quantity over here. Now what I will do is, I will look at the difference between these two. That is entry minus exit. That is m dot in x minus m dot in x plus dx. M dot in x stands for entry, m dot in x plus dx stands for exit. This value has to be equal to minus of dv times dou by dou x into u. Similarly, I can say that m dot in y minus m dot in y plus dy has to be equal to minus dv multiplied to dou by dou y times rho v. Likewise, I can say that m dot in z minus m dot in z plus dz has to be equal to minus dv multiplied to dou by dou z of rho into w. This is what I have. Now please look at all these three terms over here. What are these three terms representing? These three terms over here, they are representing accumulation of mass, accumulation of mass in the control volume. So now if I add all these three, I'm supposed to get accumulation of mass in the control volume. So now I can say accumulation of mass in control volume per unit time. This is basically per unit time. Let me mention per unit time has to be equal to how much? This should be equal to, if I combine all those things, I'm going to get minus of dv common to dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. This is the amount of volume that has got accumulated in the control volume per unit time. Let me say this has some equation number 1. Now, I can say that whatever is the mass accumulated inside over here, same has to be equal to the change in mass inside over here per unit time. So therefore, I can say that change in mass per unit time in dV has to be equal to, this has to be equal to dou by dou T of the mass inside, means density times volume. So density times dx into dy into dz. So I can write this as, now I know that this entire thing over here, stands for dV. So I can write this as dV common to dou rho upon dou T. So let me take this as some equation number 2. This, let us say, is some equation number 2. Now I know that equation number 1 and equation number 2 both are representing same thing. So I can now say that since equation 1 is equal to equation 2, therefore equation 1 was saying minus of dV multiplied to dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. This has to be equal to, equation 2 is saying dV common to dou rho by dou t. Now you see I can cancel off dV on both this. If dV cancels out and I take all the terms on one side, it implies that dou rho by dou t plus dou by dou x of rho into u plus dou by dou y of rho into v plus dou by dou z of rho into w has to be equal to 0. This equation over here represents continuity equation in Cartesian coordinate system. Very important equation. You can expect questions from here. This equation represents continuity equation in Cartesian coordinate system. Now what we can do is we can make certain assumptions and simplify these equations. Let us see some assumptions now. This was the equation we are having. Let us say case 1. If the flow is incompressible, or let us say if the flow is steady, let us start with steadiness. If the flow is steady. Now if you recall, in the case of steady flow, parameter density should not be a function of time. It should not be a function of time. If it is not a function of time, it implies that dou rho by dou t has to be equal to 0. So simplified version now is going to be dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w has to be 0. This is going to be the equation provided the flow is steady. So let me highlight this thing, provided the flow is steady. Let us take the second case now. Let us take the second case. If the flow is incompressible, if the flow is incompressible. Incompressible. Again, the word incompressible is very important over here. In the case of incompressibility of a flow, we can say that density has to be equal to a constant. Density has to be equal to constant. Neither varies with respect to time nor with respect to space. So the simplified version now is going to be dou u by dou x plus dou v by dou y plus dou w by dou z has to be 0. This actually happens to be a very, very important equation for us. The reason being, most of the time you'll be coming across incompressible flow in your examination. Sometimes in examination they can give you even a simpler form. That simpler form is you are having a 2D incompressible flow. 2D incompressible flow. In the case of 2D incompressible flow, dou W by dou Z also cancels off. So the equation now becomes dou U by dou X plus dou V by dou Y equal to 0. This is the equation in the case of 2D incompressible flow. So please remember that the actual equation is this equation. If you remember this equation, you can develop many more equations by considering the assumptions required. This is regarding the continuity equation in Cartesian coordinate system. Let us now look at the continuity equation in 1D flow. In the case of 1D flow, let us say I'm having a passage. This is section 1, this is section 2 over here. There is a fluid flowing through this passage. Let us say through section 1 I'm having some influx. Let us say this is influx. And there is some section 2 through which I'm having efflux. There is some section 2 through which I am having efflux. Now I can say in the absence of accumulation, if there is no accumulation, by law of conservation, conservation of mass, by law of conservation of mass, I can say that whatever is the mass flux at section 1 has to be equal to the mass flux at section 2. So let us say m dot 1 has to be equal to m dot 2. This is the actual format of continuity equation. Now let us move further from here to get something which is more familiar to us. Now I have already mentioned that m dot 1 has to be equal to m dot 2. M dot 1 should be equal to m dot 2. Now we know that m dot is equal to rho into area into velocity. So let us say I have over here at section 1 I am having density as rho 1, cross section area as A1 and velocity as V1. So rho 1 A1 V1 has to be equal to rho 2 A2 V2. This is the equation I am having. This is the equation I have. Rho 1 A1 V1 equal to rho 2 A2 V2. Now this equation over here is having V1 and V2 as the average velocities average velocities at the corresponding sections at the corresponding sections average velocities at the corresponding sections. Now moving further, there is a possibility of incompressible flow. So let us say the flow is incompressible. So if I mention over here, if the flow is incompressible, if the flow is incompressible, if the flow is incompressible, then what happens is density 1 becomes equal to density 2. Density 1 equals density 2. If density 1 equals density 2, I can cancel off densities on both the sides. If I cancel these densities, I am going to have then A1 V1 has to be equal to A2 V2. In other words, I have Q1 is equal to Q2. So this is the ultimate equation we have. This is the ultimate equation. But remember, this equation is valid provided you are having an incompressible flow. Only in the case of incompressible flow can you say that A1 V1 equal to A2 V2. If the flow is compressible, you will again have to go for this equation, which is rho 1 A1 V1 equal to rho 2 A2 V2. Let us start with the concept of acceleration. Acceleration is a very important concept in fluid kinematics. Questions have been asked from here. And the concept of acceleration, even though it is very simple concept in your basic mechanics, in fluid mechanics it becomes slightly complicated. We will see the reason why, but let us first define what acceleration is. Now you see, in mechanics also you might have studied that velocity in a non-uniform motion can be a function of time. It can depend on time. If it depends on time, then you can develop from here rate of change of velocity with respect to time. And this rate of change of velocity with respect to time is known as acceleration. Please remember that velocity itself is a vector quantity. If velocity is a vector quantity, its rate of change with respect to time is also going to be a vector quantity. Therefore, acceleration happens to be a vector quantity. So let us define acceleration now. I can define acceleration as time rate of change of velocity. Time rate of change of velocity is known as acceleration. Now, what is the SI unit of linear acceleration? SI unit of linear acceleration happens to be meters per second square. Dimensions, of course, are going to be very simple. The dimension of acceleration for linear acceleration is m power 0 L t power minus 2. This is a dimension of linear acceleration. Now, let us see why in our subject acceleration becomes difficult. I have already mentioned to you that the definition of acceleration comes from here. This is where you are having the definition of acceleration, that is rate of change of velocity with respect to time. In your basic mechanics, most of the time you will be given velocity in this particular format as a function purely of time. But in our subject, if you remember, we are having a possibility of velocity being a function not just of time, but a function of space as well as time. A function of space as well as time. Now, since this extra parameter of space comes in over here, due to this, differentiation does not become as simple as it was previously. That is why the concept of acceleration now becomes difficult. Let us see how to develop the equation of acceleration in the case of Cartesian coordinate system. So let us say a bit. I am now talking about acceleration in Cartesian coordinate system. Acceleration in Cartesian coordinate system. If you remember, in Cartesian coordinate system, the space coordinates are given by x, y, and z. These are the space coordinates. Therefore, I can say that the acceleration vector is equal to ax plus ay j cap plus az k cap. This is the equation of acceleration we have. Ax, Ay and Az are the components of acceleration in x, y and z respectively. I can further write that this acceleration vector, the function, let us say g of space coordinates over here are x, y and z. Apart from space coordinates, there is a time coordinate also, so t. This is the equation of acceleration. Now, I like to call this as parent vector. This is a parent vector, A vector. If parent vector is a function of x, y, z in time, the component of that vector are also possibly functions of x, y, z in time. Therefore, from here I can write down, that the value of Ax, which is actually equal to du by dt, rate of change of velocity in x with respect to time, it should also be a function possibly of x, y, z and time. Similarly, you have ay, which is equal to dv by dt. It is also possible a function of x, y, z and time. Likewise, you are having az, that is dw upon dt, which let us say is a function of x, y, z and time. So this is representing your parent vector, and these over here are representing the components of a vector. Now this is the basic of acceleration Cartesian coordinate system. Now let us derive the formula for acceleration. Very simple formula and very important formula. Now we know that Ax is equal to du upon dt. This we have already mentioned. Ax is equal to du by dt. We have also studied in the concept of velocity that the value of u itself is possibly a function of x, y, z and time. U itself is possibly a function of x, y, z and time. If I want to find out the value of du over here, du has to be equal to, now please understand, a small change in u should be developed due to small change in u with respect to x, with respect to y, with respect to z, with respect to time, and so on. So now I can say that the value of du is equal to del u with respect to x plus del u with respect to y plus del u with respect to z plus del u with respect to time. Now let me elaborate these things. This is equal to del u with respect to x is equal to dou u upon dou x into dx. What does it represent? This dou u upon dou x over here represents a small change in u with respect to x alone, that is partial derivative. Some of you might be familiar with this term as w upon wx. I prefer calling it as dou u by dou x. So please understand whenever I say dou u by dou x and so on. Now this is partial derivation with respect to x multiplied to a small part in x. Likewise, you can use analogy and you can say that this is equal to dou u upon dou y times dy plus dou u upon dou z times dz plus dou u upon dou t times dt. This is the value of du. Now if I want acceleration, I have to divide this du by time. Therefore, I can say now that the value of acceleration in x, is equal to du upon dt, which is equal to, now I take all these terms and divide by dt. So I have over here dou u upon dou x times dx upon dt plus, now these terms are quite simple, you are having dou u upon dou y times dy whole by dt plus dou u upon dou z times dz by dt. Likewise, the last term is going to be dou u upon dou t times dt by dt. Now, if you observe over here, dx upon dt is going to give you u, dy upon dt is going to give you v. Likewise, dz upon dt is going to give you w, and dt upon dt is as such equal to 1. So if I take the last term first and rearrange these things, I am going to get the value of acceleration in x is equal to, last term first I am taking, it is dou u upon dou t plus, I am taking these terms now, u times dou u upon dou x plus v times dou u upon dou y plus w times dou u upon dou z. This is the equation of acceleration in x-axis. Very simple equation. Now what I'm going to do, I'm going to use analogy and I'm going to write the equation of acceleration in y and z as well. I hope you can help me with this. Now tell me, what should the value of ay be equal to? Please observe over here. When I was writing acceleration in x, in the differential part I was keeping on getting velocity in x only. Rest everything will be maintained. Only thing is, when I write ay, I should replace this term u by v. So what do I have now? I have over here dou v upon dou t plus u into dou v upon dou x plus v into dou v upon dou y plus w into dou v upon dou z. Likewise, if I write acceleration in z-axis, I am supposed to get dou w by dou t plus u into dou w by dou x plus v into dou w by dou y. Finally, you have w into dou w by dou z. These are the terms you are going to get. Now this is representing, this entire thing over here is representing acceleration in all the three axes in Cartesian coordinate system. But before we go any further, let us divide these things into two parts. Please observe, I am having this particular column. This column over here is talking about acceleration only due to change with respect to time coordinate. Time coordinates. So I say that this acceleration is by the virtue of variation of velocity with respect to time. We call this acceleration as local or temporal acceleration. Temporal acceleration. Temporal basically means time dependent. This is local acceleration or temporal acceleration. Now if you look at the rest of the terms, so from here till the final term here, all these things combined, these terms over here, they are depending on the variation of velocity with respect to space. We call these type of accelerations as convective acceleration. Convective acceleration. Convective acceleration. Now, you tell me now that this local acceleration and convective acceleration, we are having two parts. Which part will be zero in which kind of flow? I'll give you options and you are supposed to answer me. Imagine you are having a steady flow. Tell me which acceleration is going to vanish off in the case of steady flow. Please imagine. I hope you are getting this. That in the case of steady flow, since velocity is invariant with respect to time, the concept of local acceleration will get vanished off. So now I can say that in the case of steady flow, the value of local acceleration is 0. So I can say this is going to be equal to 0 in steady flow. Steady flow. Similarly, tell me what kind of flow is required to make the convective acceleration 0? Now you see that convective acceleration is depending on variation with respect to space. Therefore, I can say that for convective acceleration to be 0, the flow is uniform flow. Uniform flow. So from here I can say that if a flow is steady as well as uniform, that time local is also equal to 0, convective also is equal to 0. This implies in the case of steady and uniform flow, I am going to have total acceleration 0. These terms over here are known as total acceleration. It is known as total acceleration. This is regarding the concept of acceleration in Cartesian coordinate system. Now let us move one step further and talk about acceleration in cylindrical polar coordinate system. Acceleration in cylindrical polar coordinate system. So let me write over here, leave it. Acceleration in cylindrical polar coordinate system. Coordinate system. Now please recall what are the space coordinates in cylindrical polar coordinate system. I hope you remember. In cylindrical polar coordinate system, the space coordinates are given by r, theta and z. These are the space coordinates in cylindrical polar coordinate system. Now, if I write the acceleration vector over here, if I write the acceleration vector is represented by AR in r cap, where AR is radial acceleration. Add to it A theta in theta cap, where A theta is tangential acceleration, and finally you are having plus AZ. You can say K cap or Z cap, anything is fine over here. So these three terms you are having. I can also mention that this acceleration vector is supposed to be a function, let us say g of r theta z n time, r theta z n time. Now, same story repeats. If the parent vector is a function of some coordinates, it is possible for the components also to be function of same coordinates. Therefore, I can write from here that AR, it is possible for AR also to be function of R theta Zn time. It is possible for A theta also to be function of R theta Zn time. Likewise, it is possible for AZ also to be function of R theta Zn time. Now we have to develop the equation of acceleration. Whatever you have studied previously for Cartesian coordinate system should help you to write the equation of acceleration cylindrical polar as well. Let us see. I am writing the equation of AR. The value of AR is equal to dVr upon dt. dVr upon dt. Recall that Vr also was a function of r theta z in time. So what am I going to have over here? The first term is the local term, that is dou Vr by dou t. Dou Vr by dou t. Now you are supposed to have three convective terms. The first convective term is with respect to r. So you are going to have Vr into dou Vr by dou r. Second term is with respect to theta. So you have over here V theta into dou Vr by dou theta. Next term is with respect to z. So you have over here plus Vz into dou Vr by dou z. I hope you are following till here. But now whatever I have written over here is having a mistake, a very subtle mistake. You are supposed to identify that. At least unit conservation should help you identify that. If you observe, you are having over here Vr into dou Vr by dou r. That is velocity into rate of change of velocity with respect to length. Fine, that is acceleration. You have over here again velocity into rate of change of velocity with respect to length. Again, that is acceleration. Fine. But look at this particular term. This is a very special term. This term over here. You are having velocity multiplied to rate of change of velocity with respect to angle. This is a problem. This is not giving you acceleration. Now you are supposed to look for the length. What is the length over here? Now you see, when you tilt, imagine that you are tilting by a very small angle. For example, you are tilting by an angle d theta. D theta angle you are tilting. The length corresponding to that angle d theta is r into d theta. Therefore, I am supposed to write over here r times dou theta. R times dou theta. I hope you are following this thing. Now this is giving you velocity into rate of change of velocity with respect to length. Length over here being r into dou theta. One more thing. When you're talking about cylindrical coordinate system, cylindrical polar coordinate system, in radial direction there is one more term developed. You have studied this in your mechanics. This term is called as centripetal acceleration. If you remember, centripetal acceleration was a radially inward acceleration. Since it is radially inward acceleration, I represent it with a negative sign. the value is equal to tangential velocity square divided by r. I hope you remember v square by r was a centripetal acceleration. So tangential velocity is v theta square divided by r. So therefore you are supposed to add over here a negative of v theta square by r. This completes the value of AR. Let us move further. Let us now talk about A theta. Let us now talk about A theta. The value of A theta, is equal to dv theta divided by dt. Now this is going to give you, I hope you can help me now. This is going to give you first local acceleration, that is dou v theta by dou t plus Vr into dou v theta by dou r, next term, plus. Now please be careful in this term. You are supposed to write over here v theta into dou v theta upon r times dou theta. I hope it is clear to all of you now. Then you have over here plus Vz into dou v theta upon dou z. Till here all the terms are clear, I hope. Then again the same story repeats. You are going to have an additional acceleration developed. That additional acceleration is known as Coriolis acceleration. The value of this Coriolis acceleration is given by v theta times Vr divided by r. So I'm going to add over here an additional term, that is v theta into Vr divided by r. This completes the concept of tangential acceleration. Finally, I am having acceleration in z-axis. The value of Az is equal to dvz upon dt. This should be very simple. There is no extra term involved in the case of acceleration in z. This is the simplest case. Please answer me. What is the first term, local term? It is supposed to be equal to dou vz by dou t. Next term, Vr into dou vz by dou r. Next term, v theta into dou vz by dou theta. I hope you got it would be wrong. I am supposed to write over here r into dou theta. Finally, I am having vz into dou vz by dou z. These are the equations of acceleration in the case of cylindrical coordinate system. These are the equations of acceleration in the case of cylindrical polar coordinate system. After having completed acceleration, the next thing we are supposed to look at is flow visualization. The purpose of this topic of flow visualization is to get an idea of how the flow is taking place. Please understand again over here, why is this topic so important for us? Why is it so difficult to visualize the flow? When you look at mechanics, basic mechanics problems, that time you are having a defined mass or defined particle which is moving in space. For example, imagine a friend of yours is throwing a ball towards you. When he throws a ball towards you, you can visualize how the ball is going to move. Probably a parabolic trajectory is going to appear. All that is fine. But imagine there are n number of people throwing n number of balls towards you. So now this becomes difficult for you to visualize. Same is the problem with fluid mechanics. You do not have a single mass or a single particle. You are having a system of particles which are randomly, independently moving, and you are supposed to visualize them. Since the visualization becomes difficult, we are going to break down our approach of visualization into various patterns, namely streamlines, path lines, streak lines, timelines, and all. Apart from this, there are many more patterns of visualizing the flow which are beyond the scope of our syllabus. So we will limit ourselves only to these patterns. Let us now start with the first pattern, which is known as streamline. Streamlines. Amongst all the four patterns, the most important pattern happens to be streamlines only. Now this might seem funny to you that even though it is the most important pattern, this is actually imaginary. So before I define it, I'm straight away mentioning you a very important point, that streamlines, the concept of streamlines, these are imaginary lines. Imaginary lines. Imaginary lines. Now let us first define streamlines, and after having defined the streamline, we will try to understand this. The definition of streamline. Let me mention over here. A set of imaginary curves. A set of imaginary curves. Imaginary curves drawn in a flow field, drawn in a flow field at a particular instant of time, at a particular instant of time, such that tangents represent the directions of velocity vector. The directions of velocity vector for the corresponding positions. For the corresponding positions. Slightly lengthy definition, but let us break down this definition to understand. First part of the definition is still here, a set of imaginary curves. So what you have to highlight is, you are supposed to highlight the word imaginary. So the pattern of streamlines are actually imaginary. Next thing, drawn in a flow field at a particular instant of time. This is the second part of our definition. Please remember, whenever you visualize streamline, you are fixing the time. At a particular time you are visualizing the streamline. This streamline, that means, can fluctuate with respect to time. Imagine you are looking at a flow right now. In front of me, let us say I'm having a flow taking place. I visualize a particular streamline. I blink my eye, look at the flow at the different instant. It is possible for the streamlines to change. So drawn at a particular instant. Now these are not randomly drawn. They are drawn with a particular objective, and that objective is, whenever I draw tangents to this streamline, the tangent is representing the direction of flow. In other words, the tangent is representing the direction of velocity vector at that particular point. So over here I can say that tangents represent the direction of velocity vector. This is the last part of the definition, very important part. Let us understand this by taking a diagram. So suppose you have a flow field. You have a flow field over here. You have a flow field over here. Let us see, this is the range of my flow. First thing I do is I fix time. Let us see, at time t is equal to nth instant, nth second, and at this particular instant, after observing the various positions, I draw a particular pattern. Let us say this is a pattern I have developed. This pattern is not randomly developed. This pattern is developed in such a way that if I draw a tangent, let us say this particular point is some position 1. This is position 1. If I draw tangent over here, let us say I draw the tangent over here. Now what is this tangent representing? It is representing the direction of velocity at position 1. Likewise, this is, let us say, some position 2. If I draw tangent to the streamline at this position 2, then this is representing the direction of velocity vector at position 2. At the same instant, mind you, this is the most important part. We are discussing for all these positions at a common instant. So likewise, if I take over here any random point, let us say some point n or position n, then this direction over here is the direction of velocity at position n. Let us say something like this. So this is known as our streamline. Now, this concept of streamline is further extended. You can imagine a bundle of streamlines now. Let us see, I am having a bundle of streamlines. A bundle of streamlines. A bundle of streamlines. And let us say this bundle of streamlines are forming a passage. They are forming a passage. Forming a passage through which can be visualized. A bundle of streamlines forming a passage through which flow can be visualized. Let us say you are having a set of streamlines, something like this. A set of streamlines, something like this. Let us say all these lines over here are, let us say, streamlines. These are streamlines. And this is a bundle of streamlines. This is forming a passage through which we are imagining flow is taking place. So let us say over here I'm having some influx, and over here I'm having some efflux. Exit is taking place. Then this particular system or this particular passage will form, it is known as stream tube. This is known as stream tube. So a bundle of streamlines forming a passage through which flow can be visualized, it is known as stream tube. Now, remember, a stream tube is bounded throughout by streamlines. So all around the stream tube you are having streamlines. From here I can get a very important point, and that is whatever properties are valid in the case of streamlines should be valid for stream tubes as well. So at this point, let us move forward to understand the properties of streamlines and stream tubes. So let us say we are now discussing properties of streamlines and stream tubes. Let us start with the first property. First property, let us say. Now tell me, can you have intersecting streamlines? Is it possible for streamlines to intersect each other? Just imagine. Let us say you are having a streamline over here. At the same instance, you are having a streamline over here. Or imagine this condition that you are having a streamline, it is intersecting itself. Is it possible? It is not possible. The reason is, at this particular point, at the point of intersection, what is happening is you are developing two tangents. You are developing two tangents. That means a particular position is giving two velocity vectors at the same instant, which is not possible because a position can only have one velocity vector at a particular instant. So from here I can declare that streamlines cannot intersect each other. Streamlines can't intersect each other. Further, I can also say if a single streamline is present which is self-intersecting, that is also having the same problem. Therefore, they cannot intersect each other, nor can a streamline intersect itself. Nor can a streamline intersect itself. So please remember this thing, there is no self-intersection possible, nor can streamlines intersect each other. Second point, let us move further. Imagine you are having a particular streamline like this, the streamline I'm having. I know that at any given point, the velocity vector is supposed to be tangential with respect to the streamline. If it is tangential, please imagine that if I look for the normal component of velocity, let us say this is the normal component of velocity Vn. That means the angle over here is equal to 90 degrees. Now this is the actual velocity vector I'm having, which is tangential. If I look for the value of Vn, how much should the value of Vn be equal to? You can say Vn is supposed to be equal to V times cos 90, is it not? V times cos 90 degrees. V times cos 90. Now what is the value of cos 90 equal to? 0. That means the value of Vn is equal to 0. What does this imply? It implies that there is no possibility of flow across streamline. Flow is possible only along the streamline. Very important point. So let me mention, flow is possible only along a streamline, only along a streamline. In other words, you can say that it is impossible across a streamline, This is the second point we are having. I hope it is clear to you. Now coming to third point. Third point, let us say. This third point over here is specific to a condition that is steady flow. We are looking at streamlines in the case of steady flow. So what happens to streamlines in the case of steady flow, let us say. Imagine in a steady flow, I have drawn a particular streamline. I choose a particular position. Let us say this position I am choosing. I know that the velocity is something like this over here. In this particular direction, this is a velocity. Now tell me, if I look at 0th second, I'm going to have this. If I look at the next instant, that is first second, since the flow is steady, the velocity is going to be invariant with respect to time. So 0th second also would give you same velocity. First second also for this position would give you same velocity. If I keep looking till nth second, at every instant this position is going to always have the same velocity. This implies since velocities are invariant with respect to time, the tangents are also going to be invariant with respect to time. This means in the case of steady flow, streamlines cannot fluctuate with respect to time. So I can mention over here, in steady flow, streamlines do not fluctuate with respect to time. Do not fluctuate or change, you can use any word, fluctuate with respect to time. This is regarding the properties of streamlines. After having seen the properties of streamlines, let us now look at the equation of streamlines. Equation of streamline is one of the simplest equations in the entire subject of fluid mechanics. And many times questions have appeared. Recently, in the past year also, we have had questions in IES examination from equation of streamlines. Let us see. Equation of streamlines. Now before I give you the equation straight away, please imagine how to develop the equation. To develop an equation, you have to go back to the basics of the definition. We know that tangent to the streamline is going to represent the direction of velocity vector. This phrase alone is sufficient to develop the equation. Tangent is representing direction of velocity vector. Hold this thought. So now I can say that if I have a streamline something like this, and if I have a tangent something like this, this is representing the direction of velocity vector. Fine. Till here everything is fine. Now what I can do is I can take a small portion of this streamline. Please imagine that this portion over here, from here till here, is a small length along streamline. Let me represent that length vector as ds vector. And of course, this line you see in the other color, in the red color, that line is representing the velocity vector. ds and velocity vector both are having same direction. Now go back to your basic mathematics. You know that when two vectors have same direction sense, their cross product is supposed to be equal to 0. Famously, it is remembered as I cross I equal to 0, j cross j equal to 0, k cross k equal to 0, likewise. So now I can say that velocity vector cross ds vector has to be equal to 0. This equation is sufficient for me to develop a refined equation for streamlines. Now what I will do is, I will write velocity vector. We know that velocity vector is equal to ui plus vj plus wk. This is velocity vector. ds vector is equal to, let us say, dx I cap plus dy j cap plus dz k cap. Now what I can do is, this equation I can write in determinant form. The determinant form is going to be I j k, and I'm having u v w, and I'm having dx dy and dz. This has to be equal to 0. If this is equal to 0, now this has come down to very basic determinant, 3 by 3 determinant. I can write it as, if I freeze this I column and I row, I can write it as v times dz minus w times dy is equal to 0. V times dz minus w times dy equal to 0. If you rearrange this, you are supposed to get v dz is equal to w dy. Let us say further, I can also write it as v upon dy is equal to w upon dz. Now freeze this j column and j row. So what do you have now? You have w dx minus u times dz is equal to 0. Again, what is implied from here? It implies w upon dz is equal to u upon dx. W upon dz is equal to u upon dx. Fine. Likewise, if you freeze the k column and k row, you're going to have finally u times dy minus v times dx has to be equal to 0, and this implies u upon dx is equal to v upon dy. Now look at all these three equations. These three equations I can write together as u upon dx is equal to v upon dy is equal to w upon dz. This ultimately becomes the equation of streamline for 3D flow. This is the equation of streamline for 3D flow. So let me mention this as equation of streamline in 3D flow. In 3D flow. Now what we'll do is, since mostly in your examination you will be worrying about 2D flow only, so we will convert this, or we will refine this to get an equation for a 2D flow. Let us see. If I want to write only for 2D flow, what I will do is, I will take only, I will take only this much part. That means u upon dx is equal to v upon dy. This is for the case of 2D flow. Now this much part, what I can do is, I can convert this part. For easier remembrance, I can convert this part as dy upon dx of a streamline. Dy upon dx of a streamline is equal to v by u. It is equal to v by u. This is the ultimate equation I prefer to remember for 2D flow. Dy by dx of a streamline is equal to v by u. What is the physical meaning of this particular equation? Dy by dx, all of you know this thing. Dy by dx is something which represents slope. So this is slope of streamline. This is representing slope of streamline is equal to what? What is slope of streamline equal to? If you look at v by u, then v by u is representing slope of velocity vector. So this is representing slope of velocity vector. Slope of velocity vector. So basically it is saying that the slope of streamline is equal to slope of velocity vector. In place of dy by dx, if I was choosing, let us say dz by dx, it would then be equal to what? W upon u. So whatever component you see over here, same component's velocity you write. Likewise, whatever component you see over here, same component's velocity you write over here. This is regarding the concept of equation of streamline for 3D flow and for 2D flow. Now let us look at the concept of acceleration with respect to streamlines. Acceleration with respect to streamlines. To understand this concept, let us draw a diagram. Imagine you are having a streamline, something like this. This is a streamline, let us say. At a particular point, I am taking as a reference, let us say the velocity is something like this. This is the velocity, let's say. This velocity over here I am representing as Vs. Suppose I move a very small distance, extremely small distance, I get another position. At this position, the velocity vector, let us say, is something like this. This is a velocity vector. Now this distance, mind you, I have chosen is a very small distance. Let us say the length of this thing, the length of this distance is equal to ds. ds is the length over here. Furthermore, the difference between these two velocities is given by dv. This is the difference between the two velocities. Now what I can do is, I can break down this dv into two parts. One component is this component, the other component is this component. This component is along the direction, it is called as dvs, and this component is perpendicular, this I call as dvn. This component is dvn. Now what do I infer from here? What do I conclude from here? Since my change in velocity is having two components, one is along the streamline, one is normal to the streamline, therefore I am supposed to have two acceleration. One acceleration is along the streamline or tangential acceleration. One acceleration is perpendicular to streamline or normal acceleration. So let me write over here that there are two accelerations. There are two mutually perpendicular accelerations developed. Now what are these two mutually perpendicular accelerations developed? The first one developed is tangential acceleration. This tangential acceleration I am going to represent by as. The second acceleration that is going to be developed over here is known as normal acceleration. This normal acceleration I am going to represent by an. Fine. Now since these two accelerations are mutually perpendicular to each other, from here I can say that the net acceleration A is supposed to be equal to the vector sum of these two, that is root over of as square plus an square. This is going to be the value of net acceleration, which is the vector sum of tangential acceleration and normal acceleration. Now let us find out the value of as and an. The values of as and an. Now to get that value, to get the value of as, I can now write, the value of as has to be equal to, this as is supposed to have two quantities. One quantity is local acceleration or temporal, second quantity is convective acceleration. The local acceleration is going to be dou vs upon dou t. Convective acceleration, if you remember from the concept of accelerations, it is velocity multiplied to rate of change of velocity with respect to length. The length over here is this length ds. So therefore, I should write vs multiplied to dou vs upon dou s. This is the formula for as. Now I am supposed to write the formula for an. The formula for an is equal to, again local acceleration I am going to have, that is dou vn by dou t plus. Now I am supposed to have convective acceleration. Please be careful over here. The convective acceleration in normal direction is given by the centripetal acceleration, which is equal to vs square by r, which is equal to vs square upon r. Now the question is, what is this r over here? Now you are looking at this small length, that is ds length over here. This ds length we are going to assume is an arc of a circle. Since it is a very small length, any small length can be assumed to be arc of a circle. Let us say that circle is having a center somewhere over here. This is a center of that circle. So let us say this over here I call as center of curvature. This I am calling as center of curvature. Center of curvature. Now, this radius from here till here is the radius of curvature. So let me represent this as some point O, and this over here is the radius of curvature, which is this R. So now I have the equations of individual accelerations, and from here you can get the value of total acceleration. This is regarding the concept of acceleration with respect to streamlines. Now let us start the next concept, that is known as path lines. Path lines. Before I start path lines, let me recall we are having two approaches. One approach is known as Lagrangian approach, the other is known as Eulerian approach. Path lines belong to Lagrangian concepts, and path lines are very familiar to us because path lines were also having some kind of reference in your basic mechanics also. Let us now define path line. Path line is basically the path traveled by a particular particle, by a particular particle in a flow field over a period of time. The path traveled by a particular particle in a flow field over a period of time. Now please be careful. We are choosing a particular particle in a flow field. Since we are using a particular particle, this belongs to Lagrangian concept. So I can mention over here, this is Lagrangian concept. So now imagine I'm having a flow field over here. In this flow field, I'm not fixing time, rather I'm fixing a particle. So let us say I have chosen a particular particle. Let me mention this particle as some particle P. This particle is P. At time t equal to 0, the particle P, let us say, was here. Now as time is proceeding, the particle P moving forward. Let us say the particle P has gone over here. This is where the particle P is present. P is present over here, and let us say the time t is equal to nth second. T is equal to nth second. Now, the trajectory of the particle or the path traveled by this particle, this is known as your path line. This is known as path line. Please understand one more thing. If this is how the particle is moving in a flow field, then tangent to the path line is again going to represent the direction of velocity vector. In the case of streamline also same thing was happening. But please be careful. In the case of streamline, the tangents were representing the direction of velocity vector of positions at a particular time. But this is representing the direction of velocity vector of a single particle at various times. So same particle is applicable. Let us say this is t1. This, let us say, is the velocity vector of same particle at, let us say, t2. This is the direction of velocity vector of same particle at, let us say, some time t3, and so on. So over here we are fixing a particle varying time. In the case of streamlines, we were fixing time and varying the particles or positions. That is the primary difference between streamlines and path lines. Moving further, what are the properties of path lines? What are the properties of path lines? So let us talk about properties now. Properties. Tell me first thing, is it possible for path lines to intersect each other? Can path lines intersect? Let us say I have a particular path line like this. Is it possible for another path line to be like this? Yes, it is possible. You see, this is a point of intersection. Point of intersection. When particle P1, let us say, has crossed this already, then let us say particle P2 has come over here. So it is possible for path lines to intersect each other. It is also possible for path line to intersect itself. Okay, so I can say that intersection of path lines is possible. Intersection of path lines is possible. But now there is a but clause over here. But when is it possible? It is possible only in the case of unsteady flow. You have to remember this thing. Why? Because if it was a steady flow, just imagine you are having a steady flow. At this particular point, if P1 got this velocity vector, P2 should also get the same velocity vector at that particular point. Because at a particular point, velocity cannot vary with respect to time in steady flow. But now I see that velocity is varying with respect to time. If velocity is varying with respect to time, I can be assured over here that this flow is unsteady flow. So intersection of path lines is possible, but only in unsteady flow. But only in unsteady flow. This is one property. Now coming to second property. Second property is a very, very important property which we are going to extend later on after streak lines also. Second property says that. Second property, it is talking about what happens in the case of steady flow. So it is talking about the condition of path line in steady flow. Now you see, if you are having steady flow, let us say you have drawn a particular path line. This is a path line of some particle P1 in steady flow. Okay. Now if P1 has moved forward, P2 would come over here, P2 also would travel the same path. P3 would come over here, P3 also would travel the same path, because velocity is not going to vary with respect to time for positions. If it is so, then the tangents over here are representing the velocities of particles, also representing the velocities of positions. That means path line is going to become equal to streamline in the case of steady flow. So path lines and streamlines are going to become identical in the case of steady flow. This is a very, very important point in the case of steady flow. Let us start the next concept, which is known as streak lines. Now to understand streak lines, I won't straight away give you definition. We will look at the diagram, and from the diagram we will derive the definition. Let us say you are having a flow field. In this flow field, let us say you have drawn a particular path line. This is a path line for say particle P1. Once particle P1's path line is drawn, you're drawing next, let us say, some particle P2's path line. At this stage, if I ask you that what kind of flow is it, steady or unsteady, will you be able to answer this? You should be actually. You are seeing that there is intersection taking place at a particular point. And we know that when intersection takes place for path lines, the flow has to be unsteady. Fine, let us move further. Suppose I have another path line for particle P3, something like this. Even this is intersecting at the same point. Let us say this is a point of intersection. So I'm having a number of particles whose path lines are all intersecting at a common point. Let me name this common point as some point O. This is some point O. At nth second, let us say, nth second, I'm having the particles P1 over here, P2 over here, P3 over here. Let us say I draw a line connecting all these particles. Suppose I draw a line connecting all these particles. Let us say P1 is over here, P2 is over here, P3 is over here, and so on. Now, what is this particular line representing? My question to you is regarding, if I want you to define this line, how can you define it? I can say it is a line drawn at a particular instant. So first thing I have understood is it is drawn at a particular instant. What is its purpose? What is it serving? It is representing the positions of all the particles which have crossed a common point in a flow field. And who is that common point? The common point is O. This particular curve is known as streak line. It is known as streak line. While all the red curves over here, these curves over here are your path lines. I'm not drawing that, it will become shabby. So please imagine these are all path lines and this particular curve is streak line. If I keep extending the streak line, I'm sorry. If I keep extending the streak line, then this streak line is supposed to end at that particular point O. Because what would happen? Path line for P4 would be something like this. Path line for P5 would be something like this, and so on. The nth particle, the last particle, would be just at point O. Therefore, this particular curve is supposed to end over here. So let us say this is for P4, this is for P5, and so on. So this curve is known as your streak line. So if I wish to define this streak line, let us say, I can now say that a curve drawn in a flow field, at a particular instant, such that it represents the positions of all the particles which have crossed a common point, which have crossed a common point. The common point in my diagram right now is this point O. So if you see over here, the first part of this definition is a curve drawn in a flow field at a particular instant. At a particular instant. That means we are drawing it only for a particular instant, let us say nth second, such that it represents the position of all the particles. You see, it is representing the position of all the particles. Which particles are these particles? Particles which have crossed a common point in a flow field. That common point over here is that point O. Is a point O. This is a definition of streak line. Moving further, there are 2 points I want you to remember regarding streak line. The first point is a family of streak lines. A family of streak lines drawn in a flow field, is known as rake of streak line. It is known as rake of streak line. It is known as rake of streak line. Now this is something which you are supposed to remember. There is no theory behind this thing. Apart from this, there is one important point. This point is probably one of the most important points of kinematics. That point again is what happens in the case of steady flow. You see, every time we are looking at some pattern which is helping us understand the flow, we are trying to observe a specific condition of steadiness. What happens in steady flow? To understand that, let me draw a streamline. Let us say the flow is steady and this over here is a streamline I'm having. Apart from serving the purpose of being a streamline, it is also a path line for me, because we have already established in steady flow streamlines and path lines are supposed to be same. Fine, it is a streamline as well as it is behaving as a path line. Okay. Moving further, imagine this is a path line for some particle P1. This particle P1 has traveled like this, reached over here. Then particle P2 is coming over here. If particle P2 is coming, let us say this is a common point O I am having. This is a common point O I am having. Now we know that in the case of steady flow, a succeeding particle will trace the path of preceding particle. So P2 also is going to travel like this. Only thing, P2 is one step behind. So if I look at nth second, P1 has reached till here, P2 is over here, one step behind. What happens to P3? P3 will travel the same path, only thing is it is one step behind P2. So P3 has come over here. Likewise, all the particles will keep following in a train, but along the same path line. And now let us say nth particle Pn is over here. Pn is over here. If I ask you to draw the streak line for this particular pattern, this is a common point. Connect P1, P2, P3 and so on till common point O. You are going to draw the same line again, which implies, now this point is very important, which implies that in steady flow, please remember this thing, streamline equal to path line is equal to streak line. Streamlines, path lines and streak lines, all of them are identical in the case of steady flow. This is probably one of the most important theoretical points in this chapter. Many examinations have asked questions repeatedly from this particular point. The last pattern we are going to discuss over here is known as timeline. Timeline. This is the simplest of all the patterns. Now, imagine you are having a particular passage. Suppose this is a passage you are having. In this passage, you have chosen a set of neighboring particles. Let us say these are all a set of neighboring particles. At time t equal to 0, these particles were present over here. At time t equal to 0, these particles are present over here. You let the flow take place. Please assume no slip condition is valid. Once you let the flow take place, next instant what happens? These particles are going to position themselves something like this. The particle over here is still over here by the virtue of no slip condition. He has moved slightly forward, he has moved further forward, he is over here, he is over here. So let us say this is at time t equal to 1 second. Next instant, I again see the flow. If I see the flow next instant, let us say the particles are positioning themselves over here. Let us say this is at second instant. Likewise, next instant, if you see, the particles are positioning themselves over here, and so on. Now, what are these lines representing over here? These lines over here are representing the positions of a set of neighboring particles at various instants of time. I repeat again, they are representing the positions of a set of neighboring particles at various instants of time. These lines over here are known as your timelines. These lines are known as timelines. All these lines are known as timelines. So how do I define these timelines now? Timelines can be defined as a set of curves, drawn in a flow field, which represent the positions of a set of neighboring particles, neighboring particles at various instants of time. A set of curves drawn in a flow field represent the positions of a set of neighboring particles at various instants of time. This is a definition of timelines. Now the question is, what is the purpose of timelines? What are they helping us understand? Now please tell me, looking at this particular diagram, when you look at this diagram, tell me whether the flow is uniform or non-uniform. If you see over here, in let us say 3 seconds, this particle has moved this particle has moved from here till here. This particle has moved from here till here. This particle is still over here. Now you're seeing that the velocity provided by these positions are not same. That means this is implying you are having a non-uniform flow. Non-uniform flow. So I can say that just by looking at the timelines, I can decide whether the flow is uniform or non-uniform. So now I can mention that timelines help in understanding. Timelines help in understanding the uniformity or non-uniformity of a flow. The uniformity or non-uniformity of a flow. This is regarding the concept of timelines, and with this we conclude the concept of flow visualization. After having seen the concept of flow visualization, our next topic is deformation and rotation. Deformation and rotation. What do we study in deformation and rotation? Now you see, a fluid element, since it is able to deform in a fluid flow, it is going to continuously change shape under the flow field that is given to it. What kind of change it is going to experience, that is going to be studied under deformation and rotation. How many types of deformation are possible? There are two types of deformation possible. So under deformation, again we are having two categories. The first category of deformation is known as linear deformation. The second category of deformation is known as angular deformation or shear deformation. Coming to rotation, under rotation we have a topic by the name rotation itself. So over here we are having a topic by the name rotation itself. Apart from this rotation, you are going to see two more parameters. One parameter is known as vorticity. It is known as vorticity. And the next parameter is known as circulation. It is known as circulation. Now, please remember that these deformations are not going to be static deformation. These are going to be continuous deformations. Since these are continuous deformation, we are not interested in the strain. We are rather interested in the rate of strain. So we'll be seeing rate of strain in the case of both linear deformation as well as in the case of shear deformation. Now let us look at some animations which will help us understand how these deformations take place. Now let us look at the case of linear deformation. We have mentioned that under deformation there are two types of deformation. One is known as linear, other is known as shear deformation. So I'm looking at a linear deformation. Let us say this is a fluid element I'm having. This fluid element over here I am representing by ABCD. Suppose ABCD is the element's name. Now you are watching over here ABCD at time t equal to 0, let us say. Now because of the velocity differences at these 4 points, what might happen? The fluid element can linearly deform. Let us see. next instant, next instant, next instant. Likewise, as the time is keeping on moving forward, this element can linearly deform. Now you're seeing over here that this ABCD has taken some new shape. Let us say A, B prime, C prime, D prime. Initially, B, let us say, was supposed to be, for example, only till here. So now what would happen? This B to B prime over here, B to B prime over here is a deformed length. So if I wish to find out later on that epsilon in x would be equal to how much? How much is the deformed length of initial length? Then I can say that strain over here is supposed to be equal to BB prime upon AB. BB prime upon AB. This would be the value of strain in x. But you see, the problem over here is AB is fixed. AB is fixed. But what about B to B prime? If you see, B to B prime initially was lesser. Later on, it kept on increasing. That means this B to B prime over here is going to be a function of time. B to B prime will be a function of time. If B to B prime is a function of time, automatically epsilon x also should be some function of time. It should also be some function of time. So I can mention it as this is a function of time. If it is a function of time, please understand that we are not going to be interested in this strain. We will be interested in rate of strain, that is epsilon dot x. This will be known as rate of linear strain. Rate of linear strain. Let us now look at linear deformation. Linear deformation. You have already seen the animation which was helping you understand linear deformation. Now let us see the derivation for the formula of linear deformation. So let me draw a diagram first. Let us say this over here is my xy plane. XY plane. I have chosen a fluid element over here. Let us say this is a fluid element I have chosen. This fluid element I am representing by ABCD. This is the element I am having. Let us say the length of AB is equal to dx. The vertical length over here is equal to dy. Now my aim is to identify what is happening after a short duration of time. Let us say the duration of time over here is dt. What is happening after a short duration of time dt? Let us say I am experiencing linear deformation. Linear deformation. To understand that, first of all, let us draw a bigger picture of this ABCD. Let us say I am drawing a bigger picture of ABCD. Suppose this is ABCD I have. Now let us say the velocities at point A is some velocity u over here, and the velocity in the vertical at point A is some velocity v. As I go forward by a distance of dx, I am having a change in velocity. A change in velocity in x. This change in velocity over here is going to be giving us u plus a small change in u that is equal to dou u upon dou x times dx. Now please remember, when I'm having linear deformation, I'm not going to have change in v with respect to x. Therefore, the value of v over here is still going to be equal to v. Moving further to moving further to the point D over here, I'm going to have the velocity over here equal to u itself. But the vertical velocity, it has changed. Let us say the vertical velocity over here is equal to v plus dou v by dou y times dy. This is the value I'm having. Now, if you observe, there is going to be, if these two terms are positive terms, there is going to be elongation over here and elongation over here. I want to identify how much is that elongation going to be. For that purpose, let us go back to our diagram. Let us say the new element formed over here, is something like this. This is a new element formed. Originally, the shape of the element was supposed to be something like this. This was supposed to be the shape. So let me define this as A. This is where B was supposed to be, but B has moved to a location B prime over here. This is where C was supposed to be, but C has moved to some location C prime over here. This is where D was supposed to be, but D has moved to some position D prime over here. Now my aim is to identify how much is this distance from B to B prime. Now if you see, this distance B to B prime over here, it is by the virtue of extra velocity developed at point B. That extra velocity developed is dou u upon dou x times dx, and you are traveling for a distance for a time dt. Therefore, this has to be equal to dou u upon dou x times dx times dt. Now, I hope you can imagine what this value is going to be equal to. Please imagine what this value is going to be equal to. This is by the virtue of extra velocity in y and multiply it to the time. So therefore you are supposed to get dou v upon dou y times dy times dt. This is the value I'm having. After having established this thing, I can now define what my deformations are going to be. So if I say that this is a deformed length and the actual lengths were supposed to be dx and dy, I can now say that the strain in x-axis, is going to be equal to how much? It is going to be equal to BB prime upon AB, deformed length upon the original length. So I can write over here this value, epsilon x is equal to BB prime upon AB, BB prime upon AB. How much is the value of BB prime? Now we see that the value of BB prime is equal to dou u upon dou x into dx into dt whole divided by length AB is equal to dx. I can now cancel off dx and dx over here. Therefore, the value of epsilon x comes out to be equal to how much? It is equal to dou u upon dou x times dt. This is a value of epsilon x, strain in x-axis. But if you look at this thing, the problem with this term over here is it is not a finite, it is not a term which is a constant. It is a function of time. It is depending on time. More the time, more variation or more strain I'm going to get. So I can say over here that epsilon x is going to be a function of time. It is depending on time. Now since epsilon x over here is a function of time, therefore over here deformation is not that important, rate of deformation is more important. So I can say over here rate of linear strain is going to be equal to how much? Please imagine. Rate of linear strain is supposed to be equal to epsilon x or epsilon dot x, which is equal to epsilon x upon dt. That means I'm dividing by time over here. If I divide this by time, what am I supposed to get? I'm supposed to get the value of epsilon dot x is equal to, if I divide this by time, I'm going to get dou u upon dou x. Dou u upon dou x. Similarly, without doing any further derivation, you can tell me the value of epsilon dot y also. If epsilon dot x is equal to dou u upon dou x, epsilon dot y is supposed to be equal to, dou v upon dou y. Likewise, you can say epsilon dot z is equal to dou w upon dou z. These are the formulas for rate of linear strain in a fluid flow. If you observe over here, for linear strain to take place, u should be differentiated with respect to x, v should be differentiated with respect to y, w should be differentiated with respect to z. So what I can do over here is, I can generalize this formula and mention that epsilon dot is equal to dou by dou. Let us say k is any random direction. If k is any random direction, then epsilon dot k is equal to dou vk upon dou k. So this is how I am writing the formula. Epsilon dot k is equal to dou vk by dou k. That means rate of change of velocity in a particular direction with respect to that direction itself is going to give you rate of linear strain. Now let us look at the case of shear deformation. Again, I am taking a fluid element over here. This fluid element, let us say, is some element ABCD. This is an element ABCD I am having. Initially, the angle over here is 90 degrees. Likewise, the angle between every corner or at every corner, I'm assuming, is 90 degrees. But because of the velocity variations at each of these points, it is possible that the fluid element can shear. For example, let us say at time t equal to 0, this is the position I'm having. Next instant, let us say like this. Next instant like this. Likewise, I keep on moving forward in time and I'm observing that the fluid element is keeping on deforming. Now please observe, this angle is no more equal to 90 degrees. I see that there is a deformation over here by an angle alpha. Likewise, there is a deformation over here by an angle beta. So this angle over here, if I say, will be equal to 90 degrees minus of alpha plus beta. This would be the deformed angle now. But again, the problem is, if this is representing my shear deformation, then please observe this alpha plus beta again is going to be a function of time. This is a story of deformation in fluid mechanics. Deformation is never static, it is going to be dynamic, it is going to be time dependent. If it is a function of time, I can say even shear deformation has to be in some way a function of time. If it is a function of time, therefore, instead of shear deformation, we'll be looking for rate of shear strain. We'll be looking for rate of shear strain. As we move further, we'll be seeing the derivation for rate of shear strain. This is only for you to get a basic idea of what is happening to the fluid element. Let us now start the concept of shear deformation. Shear deformation. Now, in the case of shear deformation, the velocity is going to vary with respect to the axis perpendicular to it. So let us draw a diagram to understand this thing. Imagine that this over here is my xy plane. This is my xy plane. Let us say I have a fluid element in the xy plane initially. So suppose this is a fluid element I am having. This fluid element, let us say I am representing as ABCD. ABCD. This is having a length over here. This is having a length over here dx. This is having a length over here dy. I want to find out what is going to happen after a small time dt, very small time dt later. What is going to happen? I want to find out. For this purpose, to understand what is happening, I am supposed to draw a bigger picture of ABCD showing the variations of velocity. So let us say I am now drawing a bigger picture of ABCD. Let us say this point over here is some point A. This point over here is some point B. This is C. This is D. Now, at point A, I am having a velocity over here which is equal to u, and over here which is equal to v. The length A to B is equal to dx. Now, in the case of shear deformation, let us say the velocity is varying with respect to every axis. So now at point B, I am going to have a velocity over here which is equal to u plus dou u by dou x, times dx, dou u by dou x times dx. Similarly, I am going to have over here a velocity. This velocity, let us say, is equal to v plus dou v upon dou x times dx. This is the velocity v I am having. Likewise, when I move in the y direction by a distance of dy, velocities u and v, both of them are changing. This velocity over here is equal to u plus dou u upon dou y times dy. Likewise, the velocity over here is going to be equal to v plus dou v upon dou y times dy. Now this is basic mathematics. All of you know this thing from functions of multiple variables. This is how the variation is going to be. Because of these variations, the shape of ABCD is now going to change. Ideally, I know the shape of ABCD is supposed to be something like this. This is supposed to be the ideal shape of ABCD. So let me mention over here the point as point A, this as B, this as C, and this as D. The distances, of course, are again going to be dx dy. But now you see over here, B is moving faster in x and faster in y. If B moves faster in x and faster in y, now what happens is, this point B over here is going to move forward in x. It is going to move forward in y with respect to point A, and now the new shape is going to be something like this. This is where you are going to have a point B prime. Or let me say, there is a point over here B prime, a transit point B prime, and this over here is B double prime. Similarly, if you observe over here this point D, the point D is moving faster in x and faster in y. Therefore, the point D has moved till here. Let me mention this point as D prime. It has moved faster over here. Let us mention this point as D double prime. So let us say this point is D prime and this point is D double prime, and this is where point D is located now. If I complete this diagram, I am going to have C prime, or let us say C double prime, somewhere over here. So now if you see, initially the shape of ABCD was something like this. Now it has deformed like this. It has deformed like this. Let us say this angle over here is equal to alpha, and this angle over here is equal to beta. These are the angles alpha and beta over here. Now, to understand the value of shear deformation, I will have to first mention these lengths, deformed lengths. I am mentioning over here, and please be with me to answer this thing. What should be the value of B to B prime? What should be the value of B prime to B double prime? Chaliye, let us start with B to B prime. How much should the value of B to B prime be equal to? If you observe over here, that is the extra distance traveled in x-axis. So therefore, it is supposed to be extra velocity in x multiplied to time, that is equal to dou u upon dou x times dx times dt. Likewise, if you look at the value of B prime to B double prime, it is extra distance traveled in y-axis, that is equal to dou v upon dou x into dx times dt. Similarly, at least now you can answer, if you are having a difficulty with this, please answer me in the case of D to D prime, similarly D prime to D double prime. What should the value of D to D prime be equal to? How much should this value be equal to? It is the extra distance traveled in y for the point D, so it is supposed to be equal to dou v upon dou y times dy times dt. Likewise, D prime to D double prime should be equal to how much? It should be equal to dou u upon dou y times dy times dt. This is the value. Now, to understand the value of alpha and beta, what I do is, look over here at this particular triangle. I can say the angle alpha is so very small that tan alpha and alpha, both of them are equal. So in that case, I can say the value of alpha is tending towards, let me write over here, alpha is tending towards tan alpha. It is tending towards tan alpha. Therefore, alpha is equal to, the value of alpha is now going to be equal to, please observe over here from this triangle above, alpha is now going to be equal to b prime to b double prime upon ab prime, b prime to b double prime upon ab prime, ab prime. This value should be equal to, this value of b prime to b double prime we know is equal to dou v upon dou x into dx into dt. So dou v upon dou x into dx into dt whole divided by a to b prime. Now a to b prime is a combination of ab and b to b prime. So therefore it is equal to dx plus dou u upon dou x into dx times dt. Now if you see in this, I can cancel off dx, dx and dx. If I cancel these things off, I can say the value of alpha is now going to be equal to, alpha is equal to dou v upon dou x into dt whole divided by 1 plus dou u upon dou x into dt. This is the value of alpha I have got. Now please observe that whatever diagrams I have drawn, they are exaggerations. They are for you to understand these values are extremely small. If they are small, I can write over here that the value of dou v upon dou x into dt and dou u upon dou x into dt, these values are much lesser than 1. If these values are much lesser than 1, please tell me, whom can I cancel? Can I cancel this value or both of them? You should be able to know that I can only cancel this part of the denominator, because what is being added to 1 over here is going to be cancelled off. But the ratio cannot be cancelled. That is not insignificant, highly significant. So therefore the value of alpha now comes out to be equal to dou v upon dou x into dt. This is the value of alpha I have. Now again I am observing that the shear deformation over here is a function of time. So I can say alpha over here is a function of time. If it is a function of time, I go for alpha dot. I am not observing alpha now, I am observing alpha dot, the rate of deformation, and that has to be equal to alpha divided by dt, and that is equal to dou v upon dou x. Similarly, you can guess the value of beta dot over here without doing any derivation. You can say the value of beta dot should be equal to dou u upon dou y. It should be equal to dou u upon dou y. After getting the values of alpha dot and beta dot, what we do is we will now define two types of shear strain. One is known as average rate of shear strain and the other is known as total rate of shear strain. So let us define over here, let us define over here two types of shear strain. One is known as average rate of shear strain, average rate of shear strain, and the other is known as total rate of shear strain. Total rate of shear strain. Average rate of shear strain and total rate of shear strain. This average rate of shear strain is given by gamma dot of xy. The value of gamma dot of xy is going to be equal to half of alpha dot plus beta dot. Half of alpha dot plus beta dot. How much should this value be equal to? So I can say gamma dot of xy should be equal to half of alpha dot is dou v by dou x, beta dot is dou u by dou y. So therefore it is equal to dou v upon dou x plus dou u upon dou y. This is the value of average rate of shear strain. Total rate of shear strain is given by epsilon dot xy. This value is equal to twice average rate of shear strain, that is equal to alpha dot plus beta dot. It is equal to alpha dot plus beta dot. So therefore the value of epsilon dot xy is equal to, it is equal to dou v upon dou x plus dou u upon dou y. This is the value we are having. Now this is a value we have got for xy plane. Apart from xy plane, we can have over here, let us say, yz plane, zx plane. How to write the formula in those cases? For those formulas, what I'm going to do, I'm going to write a generalized equation which will help you remember the formula. Excuse me. Let us say I want to write down a generalized equation for gamma dot xy or gamma dot any axis, any plane. I can write it as gamma dot is equal to half of dou by dou plus dou by dou. Let us say gamma dot mn I am writing. M is an plane, M is an axis, N is an axis, Mn is forming a plane. The moment I write gamma dot Mn, please observe over here. The moment I write gamma dot Mn, you straight away put an M over here and an N over here. Over here you put velocity in N, and over here you put velocity in M. So now this is a template we have got. If you remember this template, it is sufficient for you. It is sufficient for you to develop the gamma dot of any plane. Let us say gamma dot of yz, gamma dot of zx. I wish to write down. Now tell me gamma dot of yz. Please answer. What should the value of gamma dot of yz be equal to? Gamma dot of yz should be equal to, first of all, let me write down half dou by dou plus dou by dou. Yes, the moment I write yz over here, I am going to write y and z over here. Velocity is supposed to appear over here. It is supposed to be the velocity of z. Therefore, w over here and v over here. Similarly, over here I can write down half of dou upon dou plus dou upon dou. Yes. What do I have? Zx. Therefore, z and x. Over here, x velocity. Therefore, u. Over here, z velocity. Therefore, w. This is how we write down. Similarly, you can tell me what should happen to total rate of shear strain. In case of total rate of shear strain, epsilon dot, template I'm writing, should be equal to, half is not going to appear over here, dou by dou plus dou by dou. If I write mn, I'm supposed to write m over here, I'm supposed to write n over here, velocity in n over here, velocity in m over here. This is a template format for total rate of shear strain. Total rate of shear strain. So now if I write down epsilon dot yz, it is supposed to be equal to dou by dou plus dou by dou. Over here y, over here z. Over here I'm going to have w, over here I'm going to have v. Similarly, epsilon dot zx is going to be equal to dou by dou z plus dou by dou x. Over here u will appear, over here w will appear. This is how we write down the formulas for shear strain. After mentioning shear strain, the next thing we have to look at is the concept of shear stress. It is a concept of shear stress. So let me mention over here shear stress. Very simple concept. Shear stress. Let us say I wish to find out shear stress in some Mn plane. So tau in Mn plane. What is the formula for tau in Mn plane? Now shear stress in Mn plane is equal to mu multiplied to epsilon dot in Mn plane. Epsilon dot in Mn plane. Please remember this formula, it is sufficient for you. We have had questions from here in examinations. Tau Mn is equal to mu into not average rate of shear strain, rather total rate of shear strain. So let us take an example. Let's say I wish to find out the value of shear stress in XY plane. Most of your questions will be for 2D plane or 2D kind of flow, which is going to have XY plane in general. So shear stress in XY plane is supposed to be equal to how much? Mu into epsilon dot XY. Mu into epsilon dot XY. That is equal to how much? That is equal to mu into epsilon dot XY. Just now we have mentioned. I don't want you to watch it. I want you to check or recall how much it is going to be. I am going to write down dou by dou x plus dou by y. What will appear over here? V. And over here, u. This would be the value of tau in XY plane. Let me move one step further and close this topic of shear stress. Imagine that you are having only 1D flow. Let us say, assume 1D flow. Assume 1D flow where V is not defined, only U is defined. Let us say only U is defined. In that case, what would happen? Dou V upon dou X would be equal to how much? 0. If that happens, I can now write down the value of tau in XY plane has to be equal to mu into, let me write the entire thing again, dou V upon dou X plus dou U upon dou Y. The only thing, this time this term is going to cancel off to 0. Therefore, the value of tau xy under 1D flow conditions, please mind you, this is not in every case, this is only in the case of 1D flow. Tau xy would come out to be equal to mu into dou u upon dou y. Recall, what kind of equation are you seeing over here? You have seen this equation in the first chapter as well. This is Newton's law of viscosity. This is Newton's law of viscosity. That means from this equation, you can develop Newton's law of viscosity provided you are having a 1D fluid. This is regarding the concept of shear stress. Let us take the case of rotation now. Imagine you're having a fluid element over here, ABCD. Suppose at point A, I give a velocity of 2 units. At point B, I give a velocity of only 1 unit. The velocity at point B is lesser. So as time moves forward, what happens is A has to travel more distance in vertical in comparison to B. Therefore, eventually this element is supposed to rotate. For example, you can observe over here that as time is proceeding forward, this element over here is observing some kind of rotation. It would keep on rotating beyond the scope of our board. Just imagine that due to these velocity variations, the element is rotating. This gives the concept of rotation. Again, the rate of angular change per unit time will give us angular velocity, which gives birth to the concept of rotation. Now, we have already seen the animation for rotation, how rotation takes place, why rotation takes place. Let us now look at the derivation for the formula of rotation. Again, let us consider an xy plane where we have a fluid element. Suppose this is a fluid element we have. This is A, B, C, D. The angle over here is 90 degrees. Angle is 90 degrees over here. Let us say this is equal to dx. This is equal to dy. We have already seen in the case of shear deformation that if you are having variation in both x and y axis, then after some time dt, let us say, after some time dt, the element which should have been something like this, it takes a shape something like this. This was A, this was B, we have mentioned this as B double prime. This was C, we have mentioned this as C double prime. This was D, we have mentioned this as D double prime. Let me take this angle over here as some angle theta, and this angle over here as some angle phi. Let us say theta and phi over here. If I wish to find out the value of theta and phi, if I wish to find out the value of theta and phi, we have already done that. The value of theta and phi come by the virtue of what do you call tan theta and tan phi. So I can mention over here the value of theta has to be equal to, it has to be equal to dou v upon dou x times dt. Now this angle theta over here, I am calling it as angular displacement. This is angular displacement. It is angular displacement. Now if this theta is angular displacement, then I can say therefore angular velocity, therefore angular velocity, angular velocity, velocity, that is theta dot has to be equal to how much? Theta dot has to be equal to dou v upon dou x. This would be the value of angular velocity. Similarly, the value of phi dot would be equal to how much? Now you might think the value of phi dot would be equal to dou u upon dou y. But let me tell you, this is wrong. The value of phi dot in reality is going to be equal to minus of dou u by dou y. Why is this minus getting added over here? The reason is, please observe now. The reason is, this AB over here is rotating, it is rotating in counterclockwise direction. This counterclockwise direction is taken as positive sense of rotation, whereas AD is rotating over here in clockwise direction. Clockwise direction is taken as negative over here. So now I'm having theta dot and phi dot. After getting these values, now we define something known as rotation. We define rotation over here. Rotation is given by omega about z axis. For this particular plane, it is given by omega about z axis. It is equal to half of alpha, sorry, not alpha, rather theta dot plus phi dot. Half of theta dot plus phi dot. So now I can define this rotation as the arithmetic mean of angular velocities of two mutually perpendicular line segments in a fluid element. Therefore, the value of omega about z axis has to come out to be half of theta dot over here is dou v upon dou x. Phi dot over here is minus. Please remember this term minus over here. Minus dou u upon dou y. This is a formula for rotation about z-axis. Now what I do further is, I will now write the definition of rotation. After defining rotation, we will write a much better formula which will give you omega about x-axis, y-axis and z-axis. The definition of rotation is given by the arithmetic mean of angular velocities of two mutually perpendicular line segments in a fluid element. fluid element. The arithmetic mean of angular velocities of two mutually perpendicular line segments in a fluid element is known as rotation. Now, after having defined this rotation, let us write some more terms further to describe this rotation. This rotation over here, rotation is a vector quantity. Rotation is a vector quantity. It is a vector quantity, and this vector quantity is given, it is given by half of curl of velocity vector, half of curl of velocity vector. Therefore, we have a formula for rotation given by rotation vector is equal to half of curl of velocity vector, half of curl of velocity vector. Now, if I wish to write down this formula for rotation by taking the help of determinant, then I can say that rotation vector is equal to half of. Now, curl, when we write curl, we are going to first mention over here I, J, K, dou by dou X, dou by dou Y, dou by dou Z, and velocity vector U, V and W. U, V and W. From here I can mention the value of rotation about x-axis, about y-axis and about z-axis. So rotation about x-axis has to be equal to half of. When I want rotation about x, I'm going to freeze this I over here. I'm going to get dou W upon dou Y minus dou V upon dou Z. Similarly, rotation about y-axis is equal to half of. It is equal to half of. Now you see over here about y, that means this, if I fix, I'm going to have dou, if I fix this thing, I'm supposed to have dou U upon dou Z minus dou W upon dou X. Similarly, rotation about z-axis has to be equal to half of dou V upon dou X minus dou U upon dou Y. These are the equations of rotation. After having seen rotation, we have the next topic known as vorticity. This vorticity is given by this vector vorticity. Now, how do we define this vorticity? The definition of vorticity is quite simple. Definition of vorticity. Vorticity is defined as curl of velocity vector. It is defined as the curl of velocity vector. Now, if vorticity is curl of velocity vector, straight away I can say that vorticity vector has to be equal to 2 times the rotation vector. If it is equal to 2 times rotation vector, I can say that this vorticity vector which is equal to curl of velocity vector is supposed to have vorticity about x, vorticity about y, and vorticity about z defined. The value of vorticity about x is going to be equal to dou w by dou y minus dou v by dou z. Similarly, vorticity about y is going to be equal to dou u upon dou z minus dou w upon dou x. Similarly, vorticity about z-axis is going to be dou v by dou x minus dou u by dou y. These are the formulas for vorticity. The units and dimensions of rotation as well as vorticity are going to be same. So units and dimensions of vorticity are given by radian per second, or you have dimensions given by time inverse. These are the units and dimensions of vorticity as well as rotation. Let us now start the concept of circulation. Under rotation, we have 3 concepts: rotation itself, vorticity, and finally we have circulation. Now, this circulation is defined as this circulation over here. It is defined as the line integral of tangential component of velocity taken across a closed contour. This is a definition of circulation. Let us now look at the formula. Imagine you are having a closed contour, something like this. Let us say you have a velocity over here. This velocity over here is v. This velocity is v. Suppose the tangential component of v is given by this vs. And this vs is tangential to a small length over here. Let us say the small length over here, is this much length. Suppose vs is tangential to a small length. Let me call this length as some length ds. Now I can say that the value of circulation is equal to vs times ds integrated over this entire contour, starting from here and coming back till here. This is the formula for circulation. This is a formula for circulation. Now there is a very standard relationship between circulation and vorticity. Let us develop that relationship. So let me mention over here, relationship between circulation and vorticity. Relationship between circulation and vorticity. Now to understand that, let us take a fluid element. Let us take a fluid element. Imagine this is a fluid element we are having. This fluid element, let us say, I am taking this as some A, this over here as B, this as C, this as D. A, B, C, D are the corners of this fluid element. Let us say at point A, the velocity is equal to U, and over here the velocity is equal to V. This length is dx, this length is dy over here. The velocity at point B is given by u plus dou u upon dou x times dx, and over here the velocity is by v plus dou v upon dou x times dx. Similarly, over here I am having a velocity. This velocity is equal to u plus dou u upon dou y times dy, and over here I have a velocity. This velocity, let us say, is equal to v plus dou v by dou y times dy. These are the velocities I am having. Now I want to find out the circulation over this small area. So differential area over here is equal to dx times dy. My aim is to identify circulation over differential area dA. This is how much? This is my aim to identify over here. So let us start now. If I mention the value of differential circulation over here, it has to be equal to. Let us start first of all from here till here. The length over here is dx and the tangential velocity is u, so I can mention u times dx. U times dx. Next, from point B till point C, the length over here is dy, tangential velocity is this much, so plus v plus dou v upon dou x times dx times dy. Next, when I am moving from C till D, now this time I am moving in the direction which is opposite to the velocity, therefore I write minus. Velocity over here is u plus dou u upon dou x times dx whole multiplied to dy. Finally, I am having from point D till point A, again I have minus v times dy. V times dy. Now if you observe, I can cancel off u dx with a minus u dx over here. One moment please. One moment. I have made a mistake over here. Let me correct it. this is supposed to be dy and this is supposed to be dx. This is supposed to be dy and this is supposed to be dx, right? So I can cancel off over here. I can cancel off dx and minus u dx. Similarly, I can cancel off v dy and minus v dy. If I cancel these things off, then the value of differential circulation comes out to be equal to dou v upon dou x times dx times dy minus dou u upon dou x times dx times dy. I can further write this as differential circulation is equal to dou v upon dou x times or minus dou u upon dou y times, excuse me, dou u upon dou y times dx times dy. Now dx times dy is equal to differential area, therefore I can write differential circulation is equal to dou v by dou x minus dou u by dou y times differential area. We already know that this value over here is equal to vorticity. If it is equal to vorticity, I can then say that the value of differential circulation is equal to vorticity multiplied to differential area. So therefore, if I integrate on both the sides, I have an equation: circulation is equal to vorticity times area. This is the equation I'm looking for. So circulation is vorticity times area, or I can also mention over here as intensity of circulation per unit area is known as vorticity. Why so? Because if you can again arrange this equation, then you have vorticity is equal to circulation per unit area. Vorticity is circulation per unit area. Classification of flow based on rotation. This is the topic we are going to look at now. Let me write down. Classification of flow based on rotation. We have already discussed classification of flow, but this is a special mention. This is based on rotation. Now, based on rotation, there are going to be two types of flow. One is known as rotational flow, the other is known as irrotational flow. So let us start with rotational flow. So let me mention over here rotational flow. Rotational flow. So what do we have in rotational flow? How do we define this rotational flow? I can define this rotational flow as a flow in which a fluid element rotates about its mass center. So a flow in which a fluid element rotates about its mass center is known as rotational flow. So for the condition for rotational flow is at least one amongst omega x or omega y or omega z should be non-zero. This is the condition for a flow to be rotational. So at least omega x or omega y or omega z should be non-zero. Then we can call the flow as rotational flow. If a flow is rotational, eventually you are going to have a non-zero value of rotation, non-zero value of vorticity, and non-zero circulation also. Now what about irrotational flow? How do we define this irrotational flow? Irrotational flow. Exact opposite definition we are having. So let us say a flow in which a fluid element doesn't rotate about its mass center. Is known as irrotational flow. Again, the condition over here is going to be opposite to the condition we had over here. In this case, omega x equal to omega y equal to omega z, all of them should be identically equal to 0. For irrotational flow, all of them are 0. If all these are 0, I can further say that the rotation vector is itself equal to 0, vorticity vector is equal to 0, and circulation also is equal to 0 in the case of irrotational flow. Let us now start the concept of stream functions. Stream function. This stream function is represented by Greek letter psi. It is represented by Greek letter psi. Now regarding stream function, before I define this, please remember it is only defined for 2D flow. So let me mention it is defined only for 2D flow. Let us look at the definition of stream function. Definition of stream function. The definition states that a function defined in a 2D flow field such that it takes a constant value. It takes a constant value along a particular streamline. So a statement goes something like this: a function defined in a 2D flow field such that it takes a constant value along a particular streamline. So over here, a very important phrase is, it is defined in a 2D flow field and it should take a constant value along a particular streamline. These 2 points are important over here. Now what does it mean? It means that if this function is psi, the value of d psi has to be 0 for any given streamline. This is the meaning of d psi. Now how is it defined? Let us see. What is the formula for this psi? Psi is defined such that now you have to remember this formula. Let us say psi is defined such that the value of u is equal to minus of dou psi upon dou y, and the value of v has to be equal to dou psi by dou x. This is the equation for psi. Now apart from this equation, you can also use one more equation. And that is u is equal to dou psi by dou y, and v is equal to minus of dou psi by dou x. Both these equations are going to be valid. So basically, if you represent one with a minus, the other has to be represented with a plus. Let us prove this particular point. Now, we know that the value of psi, let us say, is a function of x and y. It's a function of x and y. Now, this implies that the value of d psi has to be equal to dou psi by dou x times dx plus dou psi by dou y times dy. Now please observe, if you take any one of these conventions, let us say I am sticking to this particular convention. If I go by that convention, dou psi by dou x I know is equal to v. So I can write over here v times dx. And dou psi by dou y is equal to minus u. So minus u times dy. So from here I can say the value of d psi is this thing. So let me highlight this equation and mark it as some equation number 1. Let me save this as equation number 1. Now let us say for a particular streamline, for a particular streamline, for a particular streamline, I know that the value of dy by dx has to be equal to v by u. Now what does this imply? This further implies that the value of v dx is equal to u dy. v dx is equal to u dy, which further implies that the value of v dx minus u dy has to be equal to 0. So for a particular streamline, we know that v dx minus u dy has to be equal to 0. Let us take this as equation number 2. Now you compare equation number 1 and equation number 2. Now, if you see equation 1 and equation 2, you observe over here that the LHS and the LHS over here are same, which implies that the value of d psi has to be 0 for a particular streamline. For a particular streamline. For a particular streamline. For a particular streamline. This is a very important point. So till here what we have seen is, for a particular streamline the value of d psi is 0 and psi is defined such that you can choose any one of these two. Now let us talk about the application of stream function. We want to see why stream function is important. Let us do one thing. Let us say I have over here a particular streamline, something like this. This is a particular streamline, and this, let us say, is another streamline. I know that along any given streamline, a stream function will hold a constant value. So let us say along this particular streamline, stream function has a value of psi 1. Along this particular streamline, stream function has a value of psi 2. Now what I do is, I choose over here a section, a vertical section I am choosing. Let us say this point over here is point 1 and this point over here is some point 2. This is a vertical section I have chosen. Let us say the coordinates of point 1 are x1, y1. The coordinates of point 2 are, since it is vertical, the value of x does not change, so it is x1, y2. This is a value. My aim over here is to identify how much is a discharge per unit width taking place across this section 1, 2. Let us define this discharge per unit width. This discharge per unit width is defined by small q. Let us say small q over here stands for discharge per unit width. Discharge per unit width. The meaning is, if you are imagining that the width perpendicular to your screen is equal to 1 unit, then it is forming an area. That area is this height multiplied to 1 unit. Across that, how much discharge is taking place, that is given by small q. My question over here is, how much is the value of small q? To identify the value of small q, what I will do is, I will first of all imagine over here a small height. Let us say this is a small height I am considering over here. This height is equal to dy, and across this height there is some velocity over here. The velocity, let us say, is equal to u. So I can now say that the value of dq over here has to be equal to u times dy. This is the value of u I am having. And I know that I can write the value of u as, dou psi by dou y multiplied to dy. This is how I can write the value of u. So now I can say dq is equal to this much. And if I integrate over here, I can say the integral should range from y1 to y2. Then I'll get the complete value of q. But now, do one thing. You look at the value of psi. Psi we know is a function of xy, which implies the value of d psi has to be equal to dou psi by dou x times dx plus dou psi by dou y times dy. This is a value. If you look over here, since the section I have chosen is a vertical section, which implies that, the value of dou psi by dou x in this particular case is equal to 0, which further implies that dou psi by dou y times dy itself is equal to d psi. Now in this place, if I replace this by d psi, then what I get over here is, I can say that integral of dq is now equal to, I can replace this entire term by d psi, and I can say its integral ranging from, now if you look over here, at point 1 the value of psi is equal to psi 1, at point 2 the value of psi is equal to psi 2. This further implies that the value of discharge per unit width is equal to mod of psi 2 minus psi 1, or you can say it is equal to mod of delta psi. This is a very, very important equation, extremely important result. And this result is giving you the physical significance of stream function. So how can I define this statement? How can I describe this statement? I can say that the difference in stream function, please concentrate at this, very important. The difference in stream function, gives the discharge per unit width, between the corresponding streamlines. Let us move further. After having understood this, let us elaborate this result. I have taken any two random streamlines over here. I mentioned that this is represented by psi 1, this is by psi 2. I had chosen previously this section, let us say this section, I am calling it as section 1, and I know that the discharge over here is some discharge Q1. If I ask you what is the value of Q1, you would say the value of Q1 is equal to the value psi over here minus the value of psi over here, that is equal to mod of psi 1 minus psi 2, or psi 2 minus psi 1, both of them are same since we are having a mod placed. Let us say I take another section over here. This section is some section 2, 2. This is some section 2. And I say that the discharge crossing this section is, let us say, equal to some discharge Q2. If I ask you what is the value of Q2, what would you then answer me? What would you then answer me? You would look at the value of psi over here. Again, it is equal to psi 1. You would look at the value of psi over here. Again, it is equal to psi 2. You would say it is again equal to mod of psi 1 minus psi 2. As a matter of fact, if you would take any random section, let us say you take any random section, suppose this is some section NN, and there is some discharge crossing this section. If I ask you what is the value of Qn, you would again say it is equal to psi 1 minus psi 2. What does this imply? This gives me a very important result from where theoretical questions can be asked, and that result is discharge per unit width across any section between two given streamlines is a constant. So if you are having two given streamlines, you take any section between these two streamlines, the discharge per unit width has to remain the same. This result is again a part of stream function's physical significance only. After having seen the concept of stream function, the next function we have to see is known as potential function. It is known as potential function. This potential function is represented by the letter phi, Greek letter phi. This is how it is represented. Now, how do we define this potential function? First of all, we start this concept. Let us go back to basic mathematics. In mathematics, in calculus, you might have studied that whenever the curl of a vector is 0, then that vector can be defined as gradient of a scalar function. That scalar function is known as potential function. So let us say you are having curl of a vector 0. Which vector are we speaking about in our subject? It is velocity vector. So let us say curl of velocity vector is equal to 0. Velocity vector is equal to 0. Before I go any further, you can tell me what kind of flow it is when I say curl of velocity vector is equal to 0. The flow has to be irrotational. So we are right now speaking only about irrotational flow. Irrotational flow. So let us say in irrotational flow, when curl of velocity vector is 0, then mathematics says that this vector can be defined as gradient of a scalar function. So now I can say this velocity vector over here can be defined as gradient of scalar function. Gradient of scalar function. This scalar function over here is known as potential function. It is known as potential function. It is known as potential function. Now, since this potential function is defined for velocity vector, we call this in our subject as velocity potential function. We call this as velocity potential function. Now, after having seen this, you can make a conclusion that velocity potential function is defined only for irrotational flow. So please remember, the condition for a velocity potential function to be defined is the flow has to be irrotational. Now, because condition is prevailing, we have one more name for irrotational flow, and that name is irrotational flow is also called as potential flow. It is also called as potential flow. So irrotational flow has one more name, it is known as potential flow. Now let us see the formula for velocity in terms of potential flow. The formula of velocity in terms of potential flow. Now, you see we have mentioned that phi over here is potential function. So let us say phi is a function of x, y and z defined only in irrotational flow such that the value of u is equal to minus of dou phi by dou x. The value of v is equal to minus of dou phi by dou y, and the value of w is equal to minus of dou phi by dou z. This is the formula we have. Apart from this formula, we can have one more formula. And that is, you can say that either you mention velocities like this, or you mention u as dou phi by dou x, v as dou phi by dou y, and w as dou phi by dou z. So the concept is, if you write minus for one value, you have to write minus for everyone. Otherwise, you are supposed to skip minus for everyone. Generally, we prefer writing minus. The reason for writing minus over here is, writing minus represents that the flow takes place in the direction opposite to the flow takes place in the direction of decrease in potential. So let me mention a note over here. The note is negative sign represents that the flow takes place in the direction of decrease in potential. So this is the purpose of writing negative sign. Moving further, after having defined this potential function, let us now talk about a set of lines along which potential function takes a constant value. This set of lines along which potential function takes a constant value are known as equipotential lines. Equipotential lines. So how do we define these equipotential lines? A set of curves along which phi takes a constant value. So this is how we define equipotential lines. Now, in the case of equipotential lines, you can say that the value of d phi has to be equal to 0. This is true in the case of equipotential lines. Now what we'll do is, we will expand this d phi equal to 0 for a 2D flow, and we will develop a result which is very important in the case of fluid mechanics. Let us see. We have already mentioned that phi over here is a function of x, y, z. Phi is a function of x, y, z. Let us say I am having over here only a 2D flow. If it is a 2D flow, I can say phi is a function of x and y. Phi is a function of x and y. So therefore I can write that the value of d phi has to be equal to dou phi by dou x times dx plus dou phi by dou y times dy. This is the value of d phi I'm having. Now, if I take dou phi by dou x as u and dou phi by dou y as v, I can say for a 2D flow, the value of d phi has to be equal to u dx plus v dy. U dx plus v dy. This is the value of d phi I'm having. Let us say I am working for an equipotential line. So now I can mention that for equipotential line, the value of d phi has to be equal to 0. What does this imply? This implies that the value of u dx plus v dy has to be equal to 0. It further implies that the value of dy upon dx for an equipotential line has to be equal to, now observe over here, dy by dx for equipotential line has to be equal to minus u upon v. Let me save this as some equation 1. Equation 1. Now, I hope you all recall that we already have dy by dx for a streamline equal to v upon u. We have already discussed this thing. Dy by dx in the case of a streamline is equal to v by u. Let us say this is some equation number 2 I'm having. Now, if I multiply both these equations, what do I get from here? I get that dy by dx of streamline times dy by dx of equipotential line is equal to minus 1. It is equal to minus 1. What does this imply? What result does it give us? If I say dy by dx of a streamline times dy by dx of equipotential line equal to minus 1, what does this imply? It implies that both these curves are going to be orthogonal to each other. So now I can say, therefore, streamlines and equipotential lines are orthogonal to each other. I'm not writing a full stop, I'm writing a comma over here. I have to continue this statement further. And that part of statement again is important. It says that except at stagnation point. Except at stagnation point. So please remember that streamlines and equipotential lines are always going to intersect at 90 degrees. That is, they are orthogonal to each other, except at the point of stagnation. I will discuss about this point of stagnation as I move forward. But before that, let me first of all show you a grid forming streamlines and equipotential lines. Let us say I'm having a set of streamlines. Excuse me. I'm having a set of streamlines. Let us say these are the streamlines I'm having. So along each of these lines, I can say the value of psi is constant. Let us say psi 1 over here, psi 2 over here, psi 3, likewise psi 4. I'm having a set of equipotential lines now. Let us say these are all equipotential lines. They are all intersecting. They are all intersecting at, let us say, 90 degrees. All of them are intersecting at 90 degrees. And I can also mention that over here, this is phi 1, phi 2, phi 3, and phi 4, likewise. Now, this is a grid formed by drawing streamlines and equipotential lines. This particular grid is known as flow net. It is known as flow net. So you can define flow net as a grid formed by drawing streamlines and equipotential lines in a flow field. That is known as flow net. Moving further, after having defined flow net, let us get back to the point of stagnation. How do we define this stagnation point? What is the stagnation point? Now remember, whenever you have a flow taking place in a particular flow, there can be a point at which all the components of velocity, they come down to zero. That particular point at which the velocities are coming down to zero, that is the kinetic energy is vanishing off, is known as stagnation point. So I can define the stagnation point as stagnation point. The stagnation point is the point in a flow field, at which all the components of velocity, drop down to zero. That particular point in a flow field is known as stagnation point. Now, recall the statement I told you some time back. It was saying that streamlines and equipotential lines are always orthogonal to each other except at this stagnation point. What is happening at stagnation point? Now, please understand that when we cannot define the velocity at stagnation point, at the time the slope of streamlines and slope of equipotential line also does not exist. If the velocity is zero, the slope of streamlines and slope of equipotential line also does not exist. Therefore, we do not discuss about the orthogonality of streamlines and equipotential lines at stagnation point. The next concept we are going to discuss is regarding the Laplace equations for stream function and equipotential functions. So let me write over here. Laplace equations for stream functions and potential functions. Now, suppose I have a case of irrotational flow. I know that in the case of irrotational flow, potential function can be defined, and then let us say the flow is incompressible. So I'm having incompressible flow. In the case of incompressible flow, we know that continuity equation says dou u upon dou x plus dou v upon dou y plus dou w upon dou z has to be equal to 0. This has to be equal to 0. And we also know that u can be represented as dou phi by dou x. V can be represented as dou phi by dou y. W can be represented as dou phi by dou z. If I put these values of u, v and w into this equation, then what do I get? From here I get that dou 2 phi by dou x2 plus dou 2 phi by dou y2 plus dou 2 phi by dou z2 has to be equal to 0. Now what does this represent? This over here represents Laplace equation, or I can say del square of phi is equal to 0. This is the equation I'm having. Now what is del square of phi equal to 0 over here representing? It is saying that if I'm having a function which is satisfying Laplace equation, then this function over here is a possible case of irrotational incompressible flow. So I can say that potential function, a potential function satisfying Laplace equation represents a possible case of incompressible and irrotational flow. Irrotational flow. Similarly, I can now talk about potential stream function. Let us say I am having irrotational flow taking place. So let me write over here. I have irrotational flow taking place. I know that in the case of irrotational flow, the value of vorticity about z-axis, which is equal to dou v upon dou x minus dou u upon dou y, has to be equal to 0. I also know that the value of v is equal to minus of dou psi by dou x, and the value of u is equal to dou psi by dou y. Or let us say I write plus over here and minus over here. There is no harm in writing this way also. Let us say I push in these values of v and u over here. What does it imply? It implies that dou 2 psi by dou x2, dou 2 psi by dou x2 plus dou 2 psi by dou y2 has to be equal to 0. Now this equation again is Laplace equation, so I can say del square of psi is equal to 0. Del square of psi equal to 0. Again over here it says that If a stream function satisfies Laplace equation, then it is representing a possible case of irrotational flow.